Good morning, good afternoon, and good evening, and welcome to the grand challenge finale of the Artificial Intelligence Machine and 5G Challenge. This is day number 2. My name is Thomas Bascoro from the International Telecommunications Union, ITU. Now, I would like to go to the first team that is going to present today. In this presentation, we're going to start with a problem statement from India. This is 5G plus AI, smart transportation. And the presenting team is STC from Saudi Telecom in Saudi Arabia.
All right, so hello everyone. My name is Abdullah Washmi. I hope that you are safe and doing great. First of all, I would like to thank you and ITU organizers for such a great competition. Today we will present our solution that is under the transportation challenge in India. Our team consists of 4 members and we are from STC Saudi Arabia. Of course, STC is the largest ICT company in the Middle East. So I will start by defining the solution. Next, please. Yes. So road conditions are one of the main causes of road safety issues. So our project aims to improve road conditions in India by utilizing machine learning to identify road defects and utilizing 5G to enable remote repairing. My colleague Noura will continue with the challenge explanation.
Here's some region insights. India has the second largest road network in the world. They used over 8 types of transportations. Last year, it has been recorded more than 4.3 million road accidents due to driving behavior and poor road condition. In 2017, potholes killed over 3,000 people in India. Lane marking are the second major issue. Financially, authorities currently are paying out more than 50 million rupees in compensation claims due to poor roads. In next slide, my colleague Athirchi will present the solution.
Hello, everyone. As my colleagues mentioned, today India has more than 4 million kilometers of road network. And to keep how we can keep the road in a good quality and in a good condition, this is one of the challenges right now every country faces. The keeping quality of roads is as important as paving the road and the implementation. This challenge is not limited only to India. This challenge every country who believing in the importance of road safety and the future of transportation and logistics. For that, we come up with a new solution. Our solution consists of 2 parts or 2 main components. First one is surveillance and monitoring through AI. The second one is fixing road problem through 5G. Can you go back, please? Yeah. In the surveillance and monitoring, we gather the data from different resources, either from taxi cars or from satellite images or any different source of data. But in this case, we prefer to go with camera on vehicle, especially in India, have more than 1 million trips per day lead by or gathered by car sharing. So no need for any investment because already the investment already exists. We will do the image analytics for the images. Once we have identify any defect or problem, the information or the problem shared to the command control center where the decision making and validation happen. The second part of the solution is fixing the road problem. The fixing road problem by 5G construction vehicle, where the vehicle drive it remotely from the command control center. India has a plan to implement 5G by 2021. From technical perspective, this is the solution architecture. The CCTV and IT sensor will be implemented in the vehicle. Then the information gonna be shared through the network layer. to the cloud, and then will be processed and do the analytics over the cloud. After that, all the information gonna be shared to the application layer. This solution will enhance to lowering the data, lowering the car accident. At the same time, will decreasing the human risk and increasing the work efficiency. At the end, it will give a highly visibility to the road line and condition for the country. Now my colleague will continue in the solution.
We're going to talk now about the system design. As you can see in this diagram, it's about the instructions and the system works. We can work from 4G to data collection, but when it comes to control a vehicle, we're going to use 5G, and it has to be reliable and low latency. Next, please. After we collecting our data, we use Google Cloud to analyze that data by object detection, and we got 79% accurate to the holes or defected areas. Also, we used Python language to identify the roads and the line on that road. And so we have a clear image about these roads. Now we can move to Abdullah, and he will talk about our platform demo and the summary of our projects.
Okay, thank you, Abdurrahman. So here we developed a prototype design for our solution, as shown in the pictures. It will cover the journey starting from data gathering, then data analyzing, work controlling by the control center, then after that, the road fixing. Next. Here, of course, we defined some qualitative and quantitative metrics to measure and evaluate our solution in future to see the impact of it. Next.
Time.
The last point is that we can link our solution with the Indian automotive industry to enlarge our scope by utilizing two streams. The first stream is the firefighting stream, as shown, and according to map of India, here are the fire points from 23rd of May till 3rd of June 2020. So we think that we can utilize this area by our solution. Furthermore, the other stream is the commercial stream by using the automated public transportation utilizing 5G, for example, the remote controlling shuttles. Then I would like to thank you for your listening, and I hope you enjoyed our presentation. So if you have any questions, please be our guest. Thank you.
Thank you so much for the presentation. I would like to invite my colleague Vishnu to moderate the Q&A. Hi, Vishnu. Good evening.
Thank you, Thomas, and thank you to colleagues in STC for that very nice, comprehensive presentation. Can I ask the judges here if they have any specific questions for the team? Yes, Amar, please.
Yeah, I have two questions. First, about the solution. I think there are autonomous vehicles now. It's very popular. And there are many companies which already had some kind of solutions, ready solutions. And what's new in your solution? Can you explain that? And second question about 5G rule in this case. It's for what? To solve problem with latency, or you have your own solution for 5G networks, or you are using only 5G networks to coverage these areas?
All right. Thank you for your questions. The first question, I would say that we benchmark about the other companies So if they have solutions similar to our solution, we found that there are, let's say, several solutions. But what is different in our solution is that we want to combine the machine learning and artificial intelligence with the 5G. See, other companies, they only utilize the data gathering about road defects and so on. Then they stopped at that level. But in our solution, we want to combine the 5G so we can utilize the remote controlling vehicles. So we want the end-to-end journey in this solution. We don't want to stop at any point. We want to cover all the journey. Yes, I hope that this answered your question.
Thank you.
Thank you. Any other judges, please? Questions? Nakao Sensei, please.
Okay, thank you very much for your presentation. I think smart transportation is a good application for machine learning. And my question is about a standardization effort. So in which area are you looking into if you want to, standardize your technology? Is it in a 5G area or application, more towards application? Because so the previous judge asked us, similar question. So in relation to a 5G technology, which kind of standardization are you envisioning now?
Let me understand you first. You're asking about which one you use, telecommunication or applications, huh? Am I right?
Yeah,
I want to understand the question.
Okay, my question is not about which you are doing, but more like a standardization effort. So what kind of, for example, study area of standardization are you looking into? Because you're presenting this at the ITU event. So I understand that you're doing a smart transportation, but in which technology are you thinking about a standardization? If you have any idea.
Okay, about the standardization, 3GPP is the organization responsible for 5G standardization, but our project is in two parts. One part into an AI and detecting any defected areas in the streets, and the other part is by fixing these defected areas by remote vehicle or remote construction vehicle that will be remotely controlled through 5G.
There is question from Leah. Leah, please.
Hi, thank you for the great presentation. And I have a question about the data collection part. And I see from your slide that the first step of your solution is collect videos and GPS using the sensor unit. I'm wondering if this data from the cars that is running on the road, right?
Hi, Leah. Yeah, exactly. We will collect the data from the vehicle.
Then I have a concern that I don't think every car owners are willing to share their data, especially this data are private data about where they have been and where they want to go. So I want to know, how do you consider this privacy thing? Thank you.
Yeah, I will answer your question today and your concern. We face the same concerns once we start the project. Collecting the data is very sensitive, as you mentioned, but here we will go with car sharing car, like Uber or Karim. India have their own company for car sharing. So they already implement the cameras. So if the government enforce the car sharing company to share the data, so there's no obstacles we'll face, because if we say it's coming from the government to private company. We think this is the best approach to collect the data. Other than this, it's a road information. We can do like the processing on the edge. So just once they see the defect, they send the information. Other than this, will not be shared. I hope I understand your concern.
Yeah, thank you. And I think if that's the case, there is also another thing concerning that I think there are too much data for a car when they are running on the road, because if a car let's say you have a car and it runs on the road an hour a day, and there are so many cars running on the road, and they are running on the road every day. So how do you deal with so much data?
Totally agree. The data is huge, so that's why we're planning to use edge computing to minimize the shared data. So the processing gonna be on the edge on the vehicle itself.
Thank you. Thank you, Leah, for that question. I just want to clarify, as of now, the solution is based on image recognition, based on Google dataset. Did I get that correctly?
We use Google machine learning tool. The data has been gathered by ourselves, and the data set that's been shared from the ITU.
Thank you
and the
so
challenge
much.
owner.
Thank you so much. Yes, we thank the presenters for the excellent presentation and the patience in explaining all the questions, answers. Back to you, Thomas.
Thanks a lot, Vishnu. And thanks to the previous presenters. Now we are going to the next problem statement. This is network status measurement by analyzing raw video data by NEC Japan. The first presentation is coming from team called Jojo.
Okay, I'm Yusuke Hashimoto from Team Jojo. Now I'm going to present about our solution. The theme of the challenge is network state estimation by analyzing raw video data from NEC. The outline of this presentation is here. First, I will briefly describe the problem statement. Recently, the demand for interactive video streaming services such as remote work systems has been increased rapidly. The internet needs to be able to cope with the high volume of traffic generated by these services and reduce the incidence of congestion. As a conventional solution, most of the related research has estimated the network state based on the occupancy rate of the playback buffer at the receiver side. However, the characteristic of interactive video streaming make it difficult to use conventional solutions. For practical use cases such as remote work systems, it's important to analyze the raw video to passively estimate the network state. This challenge is the first step to clarify the relationship between raw video and network state. The goal of this challenge is to estimate the state of the network, specifically the bandwidth and packet rate from a given raw video data. We will train our model using the video data set labeled with the network state and also perform the estimation using the trained model. In this challenge, two types of video data can be used to train and test the model: the original video data and received video data. Received video data is generated in the environment shown in the figure below. The network emulator controls the video traffic with a predetermined bandwidth and also drop packets with a predetermined loss rate. The quality of the received video depends on the network state controlled by the network emulator. Next, I will talk about our proposed solution. The objective of the proposed solution is to analyze the raw video data and estimate the bandwidth and loss ratio. The unique feature of this solution is that it estimates the degradation factor of video quality based on the bitrate distribution and trains the model using the data extracted for each degradation factor. Our contribution is to provide new knowledge to the challenge of clarifying the relationship between raw video data and network state. This is an overview of the proposed solution, which consists of 4 major steps. I will explain each step in order from here. The first step is to decompose the original video and the received video into individual frames. The next step is to calculate the peak signal-to-noise ratio for each corresponding frame of the original and received video, and to calculate the time series data of video quality. A higher PSNR value indicates less degradation and higher quality, while a lower PSNR value indicates more degradation and lower quality. Before explaining the next step, we would like to explain our focus point. In this challenge, when video quality degradation is observed in the receiver side, 2 degradation factors such as insufficient bandwidth and packet loss are mixed. Therefore, in order to estimate the bandwidth and loss rates with high accuracy, it's necessary to estimate the degradation factors observed in the received video and extract the features for each degradation factor. Therefore, we focused on the relationship between the distribution of the bit rates in the video and the degradation of video quality with bandwidth. The first feature that can be confirmed from the relationship between these graphs is that the degradation of video quality is significant, mainly during the time when the video data rate is high. Another feature is that the video degradation is more extensive for smaller bandwidths. Based on these features, the next step is extracting data for each factor of degradation from the PSNR time series data based on the distribution of bitrate. Our hypothesis is that the effect of bandwidth size will be a strong feature in the PSNR time series data during the high bitrate periods in the video. On the other hand, during low bitrate time periods, the bandwidth is less affected. In other words, only the features caused by packet loss appear strongly. Based on these hypotheses, the last step is to train and test the model by partially extracting the time series data of PSNR at high and low bit rates, respectively. Next, I would like to talk about performance evaluation. This is the environment for performance evaluation. For model training and evaluation, we perform cross-validation on the training data by dividing it into 10 parts. We evaluated the estimation accuracy of the model by the mean absolute error between the model estimate and level. Finally, in order to evaluate the estimation accuracy for completely unknown video data, we tested the model using test data generated from different video than the training data. Here are the results of evaluating the estimation accuracy of the model by cross-validation. On average, the MAE for bandwidth was about 234 kbps, and that for loss rate was 0.065%. Next, we should estimate the result of bandwidth and loss rate for the 10 test data. Calculating the MAE, the bandwidth was about 207 kbps, and the loss ratio was 0.093%. For the result of these evaluations, we can see that the estimation of bandwidth is relatively accurate, but the estimation of packet loss rate is not accurate. The reason for the inaccurate estimation of the loss rate may be that, contrary to our hypothesis, the extracted PSNL data doesn't have the feature of packet loss. One of the reasons is that packet loss is a probabilistic event. The second reason is that during the time when the data rate is extremely low in the video, there is almost no motion and the same frames are continuous. Even if some of the degradation occurs during this time period, the degraded portion are restored by interframe prediction, a video compression technique used in MPEG. Therefore, it's necessary to consider further approaches to improve the accuracy of loss rate estimation. This is a summary of this presentation. That's all. Thank you for kind attention.
Thank you. I want to ask a question before I pass it to the judges. How do you estimate packet loss? How do you calculate packet loss? At what point? That's my question. Is it from some application API, or is it a lower layer than application? At what layer do you count the packet, please?
So, okay, so I'm the co-author of this project. So instead of him, I'm gonna answer. So for project, so you want to know how we measure the packet loss rate, right?
Yes, yes.
So basically, so we focus on the bit rate, data bit rate, and we made a hypothesis. Here, you can see that. So when the bit rate is low, so our hypothesis is that so we could like estimate the packet loss rate from this value and using the PSNR, but unfortunately our hypothesis was incorrect. So our answer is the packet loss is based on the bit rate, not like how to say. Can we say like application layer level?
Okay. Yeah. That is the answer. Yes, thank you. Can I ask judges first? Carmelo, please.
Hello, good morning from Brazil. Carmelo. I'd like to know, thank you for the presentation. I'd like to know if your system can continue to learn along the process, or you just train once your model and then use it for the entire online execution.
Yes, we made a model once. Okay. It's not online, like online learning.
Mr. Ming has a question. Mr. Ming, would you like to ask? And also Hashimoto-san, it is there in the chat window. Mr.
Yes.
Ming? Yeah.
Yes. Yeah. Basically, I'm wondering why you choose video traffics for the model training and for the judgment about the network states. For my understanding, there is a lot of other type of traffics, such as FTP and email or voice. So why you choose video traffics? Thank you.
So okay, so you're right, but this challenge comes from the NAC, and the NAC provides us with data set, like only video data set. So that's why there is no option to like a video, like network traffic that we had like video traffic. No, only video.
Thank you.
So may I ask follow-on questions on this? As far as I know, NEC is how to say, it's not a network operator. So may I know the source of this video traffics? It's from the real network, or it's just simulated data?
Just simulated data.
Yeah, Mr. Ming, I think one of the slides they showed the setup where there is a simulator. Yes, thank you. We thank Hashimoto-san and colleagues for the presentation. And back to you, Thomas.
Thank you so much, Vishnu, and thanks presenters from Team Jojo. Next, we have Team KCGI from Kyoto College of Graduate Studies for Informatics.
Good morning, good afternoon, and good evening, ladies and gentlemen. Thank you all very much for coming today. My name is Yimeng Sun, and I'm going to introduce you our solution of Theme 2 from Global Round in Japan, named a lightweight deep learning model for network state estimation using raw video data. So in this presentation, I'm going to explain you the background, the problem statement, the proposed method, and finally the conclusion of our experiment. First of all, please let me introduce the background of this challenge. In the recent past, video streaming services has grown exponentially. These days, online video sharing platforms like YouTube, Amazon Prime, Netflix, and Bilibili, as well as video conferencing applications like Zoom and WebEx, has become a part of our everyday life. Especially in the situation of COVID-19 pandemic, working from home using video conferencing application has become a new normal. According to Japan Telework Association, office worker in Tokyo who works from home by telework increased from 15.6% in December 2019 to 49.1% in April 2020. However, video conferencing services need to transfer video in real time. That means video cannot be buffered like YouTube or Netflix. In this case, video quality should be optimized based on the condition of the network. The reason why is that the condition of the network affect the quality of transferred video heavily. When the network is in a good condition, the video which transferred in it can keep a good quality. Otherwise, there will be lots of noises or I say glitches in the video. So the conclusion is both provider and users are sensitive to the network conditions. In this challenge, video are being transferred through a virtual network that the throughput and packet loss ratio has been set in advance. The goal of this challenge is to estimate the network state, that is throughput and packet loss ratio, from the given raw video dataset. In this part, I'm going to show you our method to solve the problem. In this challenge, we are going to learn both throughput and packet loss ratio by classification. As you can see, with a 100 kilobyte per second of interval, the throughput of received video between 1100 and 2000 kilobyte per second can be counted into 10 classes. Then the packet loss ratio of 0.001 to 0.25 can be counted into 6 classes. So the total class of this challenge will be 60. But the given dataset only contains 480 videos and is insufficient for learning throughput and packet loss ratio at the same time. So we are going to learn them separately. Our method to solve this challenge can be divided into 3 steps. First, as we have settled the total classes, we can learning the throughput without using the data of packet loss ratio. Then learning the packet loss ratio using the data of throughput. After the learning step, we can first estimate the throughput and then estimate the packet loss ratio using derived throughput. For learning throughput, we are going to use some of the metadata of the video files. When watching this list of received videos, I just realized as the throughput goes up, the file size and the video bitrate also goes up. So throughput may have a correlation with the file size and the bitrate of received video. We have established a supervised learning for study throughput. The input will be the size and the bitrate of the received video, as well as the difference between the original video and the received one in size and in bitrate. The label, I use number between 0 to 10, which represent the throughput between 1100 to 2000. We're using neural network to deal with the learning. This is the architecture of the network. It contains 5 fully connected layers in order to take the inputs and then to predict the throughput. We are going to train this network in 2 steps. That is, first training roughly and then training carefully. The final classification accuracy becomes 96.3%. The method we propose for studying packet loss ratio is frame comparison. All the frames are being extracted both from original video and received video and compare them one by one. Then the result of comparison is being inputted to a neural network, as well as the throughput for learning the packet loss ratio. The result of frame comparison is being calculated in PSNR. PSNR is often used as a quality measure between an original and a compressed image. Compared to the other similarity evaluation method, PSNR is more robust to minor pixel displacement that often happens in video transfer. That is this case. As an example, frame A and the original frame are almost the same, you can see. So the PSNR between these 2 frames are much higher than frame B, which can hardly compare to the original one. In this experiment, PSNR is calculated for all frames in each video, and the total number of frames whose PSNR values less than some specific numbers are being counted and used as the input for our model. This is the supervised learning we have established for study packet loss ratio. The input will be the throughput, the frame count, which is PSNR less than 42, 41, 40, and 39. We are using these 2 thresholds because these have a higher correlation than the other PSNR threshold. And the label is the classes. In here, I use number between 0 to 5, which represent the packet loss ratio between 0.001 to 0.25. This is the architecture of neural network for learning packet loss ratio. We are using 3 fully connected layers to dealing with the learning. This network is also being trained in 2 steps. First, training roughly and then training carefully. The final classification accuracy becomes around 35%. Finally, is our conclusion. 2 models for learning throughput and packet loss ratio are being evaluated by mean absolute error, or MAE. The MAE of throughput has a result of 4.44. We consider this a good method to predict throughput from received videos. On the other hand, MAE of packet loss ratio has a result of 0.04. We believe this method can be improved further in our future work. Last but not least, the selling point of our model. Our model contains a precise method to predict throughput from received videos. And our model is very lightweighted. It can run on almost every platform. The third one, we only need file size and video bitrate for estimating throughput. These 2 informations are very easy to get. The last, our model calculates extremely fast. It can estimate throughput for 500 videos in just 1 second. Okay, that's bring me to the end of my presentation. Thank you all for listening.
Thank you. Thank you for that very nice presentation. Before I pass it to the judges, one quick question is about file size. Why file size is important? Why do you think file size is important?
Okay, file size and as well as the video bitrate may have a correlation to the throughput. So I think these 2 information can use to estimate the throughput.
That seems new. Okay, let me ask the judges if they have any questions. Any of the judges who has questions, please ask. please go ahead and mute. Mr. Ming, please.
Thank you. It's a nice presentation. Could you scroll down to the slides 23?
23, okay.
There's some information on that one.
Sorry, this slide?
The previous one, 22.
A previous one? Okay.
Yeah. So this is the selling point of your solution. So you mentioned extremely fast.
Yes.
So I'd like to know, in order to get the model, so you must spend some times on the training.
Yes.
Period. So I'd like to know how long it takes for the training.
Okay. Our training is just for about 300 epochs, and one epoch is just for 10 milliseconds. So the total training time is below 2 minutes, I think.
Oh, it's really fast, I think.
Yes.
So another question is, I think you use the same data set as the previous one. They both from NEC, right?
Yes.
Okay, thank you. Thank you very much.
Okay, thank you very much.
Thank you, Mr. Ming. Sensei, please.
Okay. Thank you for your presentation. I have two questions. One follow on to Vishnu's question. So you use the file size as an input, one of the inputs, but for this challenge, it's okay. But if you'd like to think about real-time streaming, there's no, the file size available. So what if you can't use the file size information? Does that affect any negative impact on your result? If you don't use file size, what would happen?
In the real time, I think as a user of, we cannot get a file size so easily. So we cannot use file size as the input. But as a provider, maybe the file size is very easy to get. So as a provider, maybe they can easily get a file size and view the bitrate, and they can predict, or I say watch, the network conditions, so they can respond very fast.
Okay, thank you. So this is out of challenge question. So I'd like to know how you respond to this kind of question. Thank you. And my second question is a very simple one. So can you show us this neural network model that you used? So you have 128 nodes in each layer, 3 layers. Yes. So how did you choose this number, like 128 nodes in the middle layers? Did you change any, this is like a hyperparameter. So
yes, this is a hyperparameter. The result is I try for every number. I try for lots of number I can think. I tried for about 32 neurons per layers to 256 neurons per layers. I tried a lot of numbers, but the result is as the layers goes huge, or say goes big, the overfitting becomes a huge problem.
Okay.
But
I see. So this is the optimal
yes,
number.
this is the optimal one.
Okay. All right. Thank you.
Thank you very much.
Thank you. I think there are interesting questions around packet loss also maybe, but I think here is Leah. Leah, please.
Hi, thanks for the great presentation. I have a question that in this solution, you used the classification approach that you divide the throughput into 10 classes and the packet loss ratio into 6 classes. And I'm wondering, why don't you use the regression?
Oh, I'm sorry.
Because I don't think the throughput is a classification thing.
Yes.
I think maybe between you know.
Yes, that's true. But in this challenge, we are the data set we get has the throughput of these 10 numbers and the packet loss ratio of these 6 numbers. So we have to use it.
Okay,
Okay, thank you. Mr. Bo, please.
Okay, thank you. I have a small question also related to the training results. So
okay.
let's turn to the page 19 of the slide. Thank you.
You mean this page?
Okay, let's look at the curve of the results.
Okay.
It seems that the accuracy is unstable.
Yes.
I wonder if I just want to know the curve is it seems like unstable.
Yes.
About the curve of the accuracy.
Yes.
Because the training in the hypothesis you use the batch size is I mean is too small. I wonder if you can with a large batch size to make the results smoothly.
Yeah. Okay.
Thank you.
The total data of we can use in this training is 480. So I was trying to use the batch size of 4 or 5, but it's just become worse. So I choose batch size 3 and 2.
Oh, okay. Thank you.
Okay, thank you very much.
Okay, very interesting problem. I think. Thank you for bringing a solution. It's quite an interesting solution as well. Thank you, Imo, and back to you, Thomas.
Thank you so much, Vishnu, and thank you to Team KCGI. Now we are going to the last team in this problem statement, Henoko King. Do we have colleagues from Okinawa?
Good morning, good afternoon, and good evening. Thank you for the great opportunity to give this presentation today. My name is Ryuma Kinjo. I'm a member of Henoko King team, and I'd like to talk our initiative, Network State Estimation by Analyzing Raw Video Data from NEC. Introduction. As you know, many business companies like travel agency, shipping company have been critically damaged under the influence of COVID-19. And people began to do stay at home around the world. So recently, the number of people using video streaming service like YouTube, Netflix are increasing rapidly. However, network traffic is so congested and sometimes occur a bad connection, video quality decrease. Here is a news of YouTube. March this year, YouTube temporarily defaulted all video to standard definition in the European Union, United Kingdom, and Switzerland. Also, Japan's situation changed clearly. March this year, the network traffic was 10% to 30% increased. Network traffics are increasing, but video quality cannot raise enough, so we needed to optimize video quality depending on network status. To contribute this problem, our team members are researching that how to obtain network status by analyzing raw video data. Look at the figure on the right. When a streaming server delivers the video to PC, there is almost no noise in the video under the good network condition. On the other hand, there is a lot of noise in video under the bad network condition. We try to estimate the network status by analyzing the noise in the video. These are YouTube 8M videos. These videos were used as materials for the video analysis. This is a procedure we use to estimate the network status. Number 1, analyzing Rgb data. Number 2, making dataset. Number 3, using neural network. Number 4, estimating network status. Number 1, analyzing RGB data. We calculated the difference of RGB data in video. We needed to know relation between RGB data and throughput before make dataset machine learning anything, so we analyze it. Low throughput like this red line, noise value will be higher. And high throughput like this blue line, noise value will be lower. The point is, when throughput decreased, the noise of RGB data was increased. Number 2, making dataset. First, prepare 2 videos which does include noise called received video and does not include noise called sending video. Then divide 2 videos into frames and divide into 64 images from frames. Next, the RGB information of the sending image and the received image are extracted. We compare extracted RGB data from sending image and the received image. And received image, if received image exceeds the threshold, it is recognized as a noise image and added to the noise dataset. Some of the images from sending video are added to the non-noise dataset. Now I will explain to you about threshold. RGB data has 0 to 255 value range. And these pixels are arranged horizontally and vertically. And theta is now currently set to 25%. So if difference of sending image and received image exceeds this formula, received image is added to non-noise dataset. Received image is added to noise dataset. Number 3, using neural network. We developed CNN construction so that detects noise in video. First, input image in input layer. And the kernel size is 6 × 6. Second, these 2 convolutional layers extract what features the image has. And then reduce and adjust data size in the max pooling layer. And last, fully connected layer will judge whether input image is a noise or not. And this table is the accuracy of our CNN. We adjusted parameter of the kernel size and number of neurons. The best model accuracy was 77%. Number 4, estimating network status. We estimated the network throughput using our developed CNN. The left table shows the noise ratio in video. Look at the values. Network throughput increase, noise value is a little bit decreased. The right graph shows the relation of throughput and noise. Red points are noise value, and the green line is the best estimate throughput function. And the difference between plot value and green line value is used in this formula. As a result, MAE was 196.8 kilobit per second. This means that when estimate the throughput, there will be an average difference of 196.8 kilobit per second from the actual throughput. We basically succeed to estimate throughput, but we can't still estimate packet loss ratio yet. So our team tried to estimate it using PSNR. PSNR is a technique that calculates the amount of noise in image. Under 30 is really noisy image, and over 40 is really clear image. We just try to estimate packet loss ratio using PSNR like this. These values are PSNR of video. Unique aspect of our team's work. First, we made dataset based on RGB data. We just calculated the difference to RGB data, that's simple. And we created our CNN and revised CNN code so that improved estimation accuracy. And we estimated throughput using Excel. We're not use any complicated methods or structure. Pick up calculated data from CNN and make optimum linear function using Excel. Analyze RGB data, use CNN, and make function using Excel. That's our simple estimation method. That's all my presentation. Thank you for listening.
Thank you so much for your presentation. Now we go straight into the Q&A session. So welcome, Vishnu. Welcome back.
Thank you. Before I hand over to the judges, I want to ask Kinjo-san,
yes,
if the RGB method that you have used, RGB analysis method, has it been used before or in any of the papers that you have analyzed? Have you added reference in your report or GitHub or somewhere? Could you please tell us if this is your innovative approach or has it been used before in any context? Not specifically in this solution I'm asking, in this problem I'm asking. In general, for throughput or packet loss estimate, has RGB method that as you show here been used before?
Thank you for asking, but I'm sorry, I don't understand your question. Could you repeat again? Sorry.
I will try and put it in the chat, but also I will repeat. The question is the RGB method that you show here for throughput
RGB method,
estimate.
yes.
Yeah, is this your own solution or has it been used in any papers before? Is it published before?
Yeah, no, that's our method, not publish any paper or any, you know.
Thank you. And
thank you.
yes, I will come back to this data set later, but let me just first give preference to judges. Any questions from judges, please? Any of the judges? Yes, please.
Thank you for your presentation. I have a question about the kernel size for the neural network. So let's turn to the page. Yes. Thank you, Lisa. So far as I know, I think in the convolutional neural network is usually use the kernel size with the odd number. For example, 1 multiply 1, 3 multiply 3, or 5 multiplies 5. And in your report, you also use the even number, such as the 4 and 6. But in my to my knowledge, I think the reception field of the convolutional when we're using the even number is too hard to find the central of the reception field. Is there some special consideration when we to choose the kernel size? Thank you.
So you want to know why our team choose even number? Is it correct?
Yes. Okay.
I don't have knowledge of kernel size. I don't know why odd number is good. Sorry. So just curious, our curious. Kernel size bigger and accuracy of our CNN is higher or not. I just want to know. Accuracy.
Okay, because in the CV field, the older number of the kernel sizes are widely used because of we can easily find the central of the reception field if we use the old number. So it is easily to smooth the slide window. We can easily find the central of the reception field. If we use the even number, I don't know because so far as I know, we seldom paper are reported to use the kernel size with even number. So I'm so curious about why we choose the kernel size. Thank you.
I don't know either, but thanks you your advice.
Okay, I think it's really quite a good idea. Thank you.
Any other questions from judges? I want to ask Kinjo-san about the data set. Are you planning to open it, or is it a private data set?
I send GitHub link, for this competition. So yes, that's public data set, and you can, if you run Python code, my Python code, you can create data set just like my data set, my RGB data set. Did you understand it?
Yes. Thank you.
Thank you.
Thank you. Anybody else? Any other participant who has questions? No, in that case, we are back to Thomas. Thank you, Kinjo-san.
Thank you for a great opportunity.
Okay, next up, we are going to the next problem statement, which is compression of deep learning models. This is an enablers track, and we are going to start with AI Maghreb.
Okay, good afternoon, evening, everyone. I'm Wang Yuwei from the Institute of Computational Technology, Chinese Academy of Sciences. Now, I would like to present our solution research work with my partner, Dr. Sun Sheng. And our presentation, the title of presentation is N-Age Cooperative Inference of Deep Learning Model based on DNN partition. There are 6 parts in our presentation. Firstly, I will introduce the research background. As smartphones are made more personalized and intelligent, the wearable devices and the smart home devices have become more and more popular. And the interaction model among mobile service is changed rapidly. However, when the reference of DNN is executed on the cloud data center, huge amount of data must be uploaded to the cloud, and the transmission time is too long. For the second part, the results of the mobile device is still limited. So running the DNN model independently will lead to high computation latency and high energy consumption. In order to overcome the limitations of traditional cloud computing model, mobile edge computing will push the computing power down to the edge of the network and execute DNN model inference through edge-edge collaboration mode. During the edge-edge collaborative inference processes, how to automatically divide DNN computing tasks between edge devices and how to reduce the end-to-end inference latency are important research issues. It just was a problem we want to solve in our solution. Next, let me move on to the second part to introduce some research works. There are 2 kinds of existing estimation solutions. The first one doesn't use any prediction model, and the other one is to establish a regression model of layer to predict computation latency. Through our analysis, we can draw a simple conclusion that the existing strategies don't consider the change of load of devices when estimating the computation latency. The estimation of the computing latency is not accurate when other tasks are running the devices. Next, we'll provide our research objectives and context. The aim of the research on deep learning model end-to-edge collaborative inference is to optimize the end-to-end inference latency and improve the collaboration efficiency of end-to-edge devices. The one is to provide DNN partition algorithm, and the other one is to set up a computation latency prediction model adapting the device load. Now, we have already an ITU standard F.AI-DMPC and development on typical framework for deep neural network model partition and collaboration execution in ITU-T studying group 16, question 5. Next, I will introduce our solutions briefly. First, we formalize the DNN partition problems formalize the DNN partition problem first. For DNN which have n layers, MI and EI represent whether the IS network is executed on n devices or n devices respectively, which are binary variables. The characteristics of DNN partition problems are deposable and have the optimal substructure properties, so it can solve by dynamic programming algorithms, which is short for DP. Consider a DNN model with n network layers. They are labeled as 1, 2, 3 until n, according to the topological sorting. First, we divide the algebra DNN partition problem into two subproblems. Subproblem 1, when the ISDN layer is executed on the device, we aim to minimize the inference latency from input layer to the ISDN layer. The optimal solution of these subproblems is denoted as OPT mobile I, and subject problem 2 also described like OPT HI. Next, we choose 4 typical kinds of structures for the typical DNN model, depending its complexity in structure. The first one is simple chain structure, like the picture in the slide, and some more complex branch structure 1, branch structure 2, and until the final complex branch structure like this one. From for all these 4 structures, we can conclusion that there are 4 possible sources for each optimal solution of the recursive expression for the branch source node to the branch sink node. Take the OPT mobile of the branch sink node as an example in the slides. It may be one of the 2 cases in which the branch source node is executed on the end device, or it may be one of the 2 cases when the branch source node is executed at end device. There are 2 cases in which the branch source node is executed by the end device. One doesn't need to transmit the output of the branch source node, and the other needs to transmit the output of the branch source node. Now, we move on to introduce the second part of our solution, the computing latency prediction model. Compared with some related works about the CPU and the memory load of device are considered in our solution. And in order to make the prediction result adapt to change of device load, the dynamic characteristics related to the load are introduced for the first time, such as the ideal CPU time, the system CPU time, the CPU utilization, the CPU utilization, and so on. In order to evaluate the gain of the dynamic characteristics, the logarithmic regression model and the linear regression model used in the existing prediction model are reconducted. the regression model selection, pair model computation doesn't include better results because a complex regression model may lead to overfitting. So our times a variety of common regression models with different complexity, including the linear regression, the lasso regression, the reed regression, and so on. Okay, let's move on to look at the experimental results. In order to verify our solution, we have already set up a testing framework in our laboratory. According to the device, we choose MacBook Pro to simulate the edge device and the Huawei mobile phone as of 3 and 4 and recent network rating refers to measure the network speed of more than 1 according to the signal. Choose 14D models to test now. And in the first experiment, we can see and connection is unstable. Okay, so now it's okay. And the result of the first experiment, we can see that the performance of the final scheme observation has greatly improved compared with the relative work to surgery. And this experiment is just for simple chain. And we also do some more experiments according to the non-chain structures. We choose 4 benchmarks. One is neutral solution, and the 2 is ADS, and another 2 is addressed to only the N devices and only the H devices. We can see that all the experiment results, we can see that our solution have improved the performance compared with benchmarks. And the final one, the figure shows the partition location of the PX2 and Wi-Fi and partition location of chair and fold and ratio work. It can be said that if the entire branch structure is simply partitioned as a whole, then the optimal solution of end-to-end inference latency will be imposed in these 2 scenarios. That's all for my report. Thank you for listening. Thank you.
Right now, we go direct to the next presentation.
Yeah, okay. Hello, everyone. Thanks for gathering. I hope everyone is doing fine during the pandemic, and we thank ITU for organizing this challenge amidst the pandemic that's going on. So it was a wonderful experience participating in this. So yeah, with that introduction, our objective, our topic is to compress deep learning models. That is the race that we are all running towards at this point. And I'll just like to introduce our team before getting into our work. And we are a team of undergraduate students, 3 undergraduate students, where we are mentored by our mentors in Ericsson Research. And before getting into the presentation, what if I tell you could potentially compress a deep learning model to like 60% or 61% of its original size? Or what if I tell you like you don't need any special hardware to execute it? And what if I tell you that you could deploy it in any edge device at the same time that can generalize much better than a teacher model, and that could do it in a very less energy? These are some of the open questions, and these are kind of intriguing. To explore these questions, let's get into this presentation. So with an advent of 5G that's coming up everywhere, the pressing need to compress deep learning models is a buzzword around all over the world. So we also ran in the same race, and we tried exploring few prior arts, which is like model pruning, model quantization, and knowledge distillation. And exploring all this, like a sudden thought that came to our mind is like, okay, there are so many compression the techniques available, but why aren't these so prevalent? So in this, we tried picking up knowledge distillation as our topic, and we understood that though knowledge distillation is having a lot of perks of its own, but a single teacher's model, which is like a traditional framework of knowledge distillation where you have a teacher and your student, a single teacher model cannot effectively distill its knowledge to all the kinds of, one teacher cannot distill its knowledge to any kind of a student. For example, there could be so many data variations that could be coming. Maybe a huge teacher can handle it, but a single student, a small student cannot potentially handle it. So how to overcome this problem? When we are coming up with an edge device, we need to overcome these kind of problems. So to solve this problem, to effectively make sure that the knowledge distillation can work as a universal solution for any kind of deep compression, we tried exploring this framework where we tried coming up with a novel architecture and knowledge installation called multi-student knowledge installation. So in this, what we did was we potentially, this is the framework what you're seeing on the slide is nothing but a traditional framework where a teacher model is distilling. Teacher model is potentially a huge model, and it is distilling its knowledge to a student model. So this is a very traditional framework. So before getting into the architecture, I'll just say the data set that we use to give a standard clarity. Like we use the Cypher 10 data set, which is like a well-known data set. And here you could find the standards like GPU we used. And here you could see the high-level architecture of our approach. So what we did, the traditional knowledge registration works in this way. Either you have a teacher and a student, or you have a teacher, a teaching assistant, and a student. So these are some of the most prevalent methods that are found. But all these have its inherent problem. So like I mentioned, a teacher and a student, one student cannot predict on all data. Like it will fail on some data points. And if you have a teaching assistant to distill the knowledge further, it is more computationally expensive. The moment a teaching assistant comes, you need to train 3 models. So what we did was we trained a teacher and parallelly 2 student models. They both will be learning on different data distributions. That is how we train this model using a novel loss function. So once we executed this, we have a teacher model and we have 2 student models, which can predict on completely new, which can predict on different data points. And this can also accommodate to like new variations that is coming. So once we have this, we didn't stop at that point. We also appended another architecture where we had 2 students and we made both the students predict on the Cypher 10 data set. So once we asked the students to once we asked the student to predict on the Cypher 10 data set, we understood which student is working better on which data. But also in this, we found an interest, and then we trained a model selector which can understand that which student is working better on which data distribution. So potentially this model selector will be able to find out which is the winning student for a given image. So once from this ground truth, we were able to propose a standalone architecture, which is our third novel component. So once we bring in this, all we need here is we can eliminate the teacher. We can just bring in input image data, and you can just feed it to the model selector. The model selector has the ability, the knowledge to map the input data attribute, which I mean, as a human, we couldn't map, to the architecture of the student model. So once we have this mapping, we are like the moment the input data comes, it will be routed to one of the student models only. So in this way, we could train multiple student models in edge devices, and this can potentially help in scaling for like as the world is moving towards active paradigm. We need this kind of a scaled architecture, like to work on any kind of an incoming data distribution, and the model that works only based on that is something that we need. So this architecture is something that we proposed, and that is working well. And so here to give you a rough idea of our meta architecture, so here we have a teacher model, which is ResNet 50, and the 2 student models which we used, which are like DenseNet 121 and Inception GoogleNet. Model attributes, here you could see that the teacher is an extremely lower parameterized model, like it is around 25.6 million parameters, but the students are potentially in 3.27, 6.07. And the model selector we use is a very lightweight CNN model that can be easily deployed in any edge device, which is nothing but 0.55 million parameters. So here you could see the workflow. So this is a traditional pipeline of knowledge distillation, but we came up with those architectures to make sure this aligns with our work. And here you could see this result. This is where the most interesting part comes in. So here you could find that both the student models are acting complementary to each other. For example, where student model 1 works better for one class, student model 2 doesn't work better on that class. So this trend is found towards all the classes. And another interesting observation that paved way for us to reinforce on the model selector is the moment you augment the student models with the model selector, the model selector with the student model is performing much better than all others. Except the truck, you could find that model selector is winning at all the positions. So we are not we are saying that this could be this could take us a step ahead towards like making knowledge distillation as one of the good solutions towards model compression. So we would like to elaborate on the compression which I initially spoke about. Here you could see that like when you just take like we have proposed a compression on 3 parameters. One is computing efficiency and reduce memory footprint at the same time. So here we have proposed that GoogleNet, which is like so here you could, the percentage value you are seeing is it is 87.3% compressed to its original size. So Yeah, it's 87.3% compressed to its original size. So here you could find all the models results. So here you could see that even in the overall compression stage where we have all the three models, the compression is around 61.4% and space consumed is 40.61%. So another question that could come is like, why did you choose these models? Which I already explained about the student models. Like, why did we choose? They were acting complementary to each other. But the model selector, we chose it again by empirical studies, where we found that 2-layer didn't work well. It was having poor generalization. 4-layer was having poor generalization, though they were performing well. So 3-layer was giving good performance, at the same time good generalization. Here you could see the table on the right side. So we chose it by empirical study. And here you could see the results, where you could find that the ResNet 50, which is like the teacher model, which is like highly over parameterized, is 81%. But we are gaining model selector plus student 1 and 2. We are gaining a more accuracy, like 81.79%, by achieving a very huge margin of compression, which is around 61 to 85%. So after achieving that much high margin of compression, still we are getting a better accuracy. The reason for this is ResNet 50 is highly over parameterized. It could learn any unwanted data distribution also. It could learn anything that's coming in. But model selector is highly selective and it will only learn what is most needed. And this kind of helps us in generalizing better, which is most needed for our current world. Like since new data is coming, we need to be generalizing very quick. So this is, we have proposed the same architecture in ITU format, which is something that's much needed here over here. We have proposed both the architectures in ITU format. And we have also proposed an edge implementation over network, which could be used in 5G application scenario where we could deploy it in an application cloud. So here we would like, before going to conclusion, I would just like to show our novel loss function that we proposed, where you could see that this loss function where we had lambda 1 into distillation loss by lambda 2 into loss of, like the loss of student 1 and student 2 was in denominator. So this kind of made sure that both the student models learned not the same data distribution, which is like going to cause energy loss. Here it learned different data distribution. So both the student models can accommodate to different data attributes or geometry, which is very needed or which is kind of difficult in to identify in images, and our model is able to do that. So this new loss function was able to help us do that part. And on overall conclusion, I would like to say that I mean, knowledge relation is not a universal solution, but this could definitely take us a step towards achieving where we want to be towards model compression. And as the world is moving more towards an active learning paradigm, where we do not know the amount of, where we do not know the distribution of data that's coming towards us, we're not aware about the data geometry or data distribution. So we need to be highly adaptive and dynamic towards carrying out any kind of an inference. So we need to reduce the inference time. So for that, we need models to work very well on a given data distribution. So for that part, we are trying to use this kind of a multi-student architecture. At the same time, using training, like inferencing using a multi-student architecture parallelly is able to reduce our inference time to a great extent and promote a very big compression. This could be potentially implemented in any kind of an edge device. Like it could be even implemented in Google's reinforcement learning algorithms, where your device might need a completely personalized predictions than another person's device. So we could potentially use such models over there. At the same time, this is simple deep learning model. So this does not require a special hardware to be trained upon. So just to prove our hypothesis, we tried with a couple of data sets, and here we have shown the data set for one of them, which is Cypher10. So we would like to say this, call this architecture as multi-context aware architecture, which is potentially aware about the context of the data. So context of what is coming. At the same time, it is able to map the input attribute to the model's architecture. So this promotes a huge amount of compression. So this is something that we really believe in. And we believe that like once we have this implemented in different application clouds or other architectures, this can potentially help us in like increasing our inferencing, decreasing our inferencing time drastically. So this is what we are thinking. So, and just to reinforce on this loss function, this lambda 1 is nothing but a normal, yeah, sorry, yeah, this lambda 1 is nothing but not like a normal weightage point that we gave, like it's just a weight metric. And you have the distillation loss, which is the distillation loss between the student and the teacher. And the same time, lambda 2 is again a weightage function. But on the denominator, you have the loss of student 1 and student 2, which will, as the loss increases, this value will decrease. So potentially, we are able to make sure that both the student models are not learning the same data distribution. So in this way, we are able to solve the traditional problem that occurs in knowledge distillation pipeline, where we have the student, either we have one student model trying to predict everything, or we have a teacher model trying to distill. So with this, I would like to conclude my presentation, and I would like to thank everyone for the opportunity.
Thank you so much for the presentation. Now we would ask Vishnu to moderate the Q&A. Please, Vishnu.
Thank you.
And to all the upcoming presenters, please make sure that you are keeping time so that we can finish the program according to the plan. Thank you.
Thank you, Thomas. Setu, first of all, excellent presentation, and thank you for the mentors as well. I see them. Before I pass to the judges, one quick clarification question from my side. Would you call your solution compression or distribution? Because in your solution, you have basically introduced this selector and the student models, which are basically trained on different types of classes of data sets and doing inference on different classes of data sets. So is that a partitioning problem, or is it a distribution problem, or a compression problem? Could you comment before we take the judge? Maybe it will become a bit more clear for the judges based on your comment.
Okay, yeah. Thank you, sir. Thank you very much for the question. So we would like to pose it as a compression problem, because when you see it from a teacher-student perspective, it might appear like a partition problem. But when you remove the teacher model, when you see the standalone architecture, it is a compression. It's basically a compression task where the teacher model is heavily parameterized, but the model selector plus the student models are a compressed version of that model, but still able to perform much better than them. So we would like to hypothesize it as a compression architecture.
Thank you for that clarification. With that, I would like to open for judges to ask questions. Please, any of the judges, if you have questions, this is the time. If meanwhile, while we are waiting, you had a bar chart, Setu, in one of these slides, you had a bar chart. Yeah, and you mentioned that, there was a graph with a bar chart, which showed, I think the slides are moving slow, but my question in the bar chart is that, you mentioned, yeah. So model selector is also here. Why so actually? Why do you have model selector also competing for accuracy with the others here? To me, it is a little strange that model selector is also competing here with as one of the bar charts. Could you explain a little bit why it is here?
Yeah, sure, sir. So the reason we have but model selector is here. Yeah, maybe I should have explained at that time. So the student one is nothing but just a standalone student one. Like you just have a teacher and like student one performing. Student two is just student two performing. But model selector is along with student one and two. Like if they work parallelly, like you feed in an image data, our model selector will be able to say that which model is working best. So it will feed the image only to that corresponding model. So we have given that accuracy, and we surprisingly find that that time the accuracy is pretty high. Even if the student who predicts at that time, the accuracy is high. So that is why we have put it as like 3 different bar graphs.
Yeah, thank you. So I think this solution divides something into the model selector, and I'm wondering whether there is some relationship or difference from that of federated learning. As far as I know, federated learning it's many devices do the machine learning for some purpose. They cooperate on some basis. So is there any difference from that? Thank you.
Thank you for your question, sir. So federated learning will be, multiple edge devices will be working in a decentralized manner. So here, you could potentially have, you could implement federated RL and everything. It will work in a decentralized manner according to the device. But here, what we are trying to do is the difference. What we would like to propose is that the model selector is not like a federated architecture exactly. Maybe you could, like, on a high level, you could view it like that. But here it's about understanding the data distribution and mapping it to a place where the data can be inferred in a less time, at the same time in a best possible manner. But federated learning would be potentially like the device customized thing, something like that. So like that on a high level, maybe they appear like same, but they are we would like to say that they are different because there is no mapping happening in that. But here you have a mapping between like the thing that we want to infer and the thing that is getting inferred. So we would like to hypothesize in that way.
Thank you. We are out of time, so we can take the other questions on chat. Back to you, Thomas.
Thanks a lot, and thanks to the presenters. Now we are going to the next problem statement. This is privacy preserving AI and machine learning 5G networks for healthcare applications.
Hi, everyone. I'm presenting our submission to the privacy preserving AI ML in 5G network. Our solution is called Dopamine, a differentially private method for federated learning on medical data. We are from Imperial College IPC Lab. I'm Mohammed, and I'm presenting on behalf of our team. Assume that a patient goes to a hospital and make a medical image like from retina. And a doctor who's expert in this area make a diagnosis, make a diagnosis on this image to see whether there are any sign of disease or not, or what type of disease. And every hospital has many patients, and so there are some data sets. The motivation is, can we use these data sets to train a deep neural network so we can use this neural network for example, automated diagnosis, for which bring us many advantages, like we can cover more patients, we can do it faster, cheaper, and lower the burden on healthcare systems. The challenge is that these data sets are distributed among these different locations, and privacy of the patients are as important as the patient's health. And even there are some law restriction on collecting this data. So the solution is to train this deep neural network via federated learning through a central agent like a public health service. So after training such model, a new patient who has access to a good communication network like 5G and has a medical image, but don't have access to a good doctor, can query on this model and make a prediction on their data. And we define the utility of this model such that we need it to be as accurate as possible, that this prediction on the image is similar to having a diagnosis via an expert doctor. But to achieve this kind of utility, we also need to consider privacy. There are two types of privacy concerns here. First of all, we need to make sure that during training of this model, we don't leak information about any patient. So this model is trained such that we satisfy differential privacy, which I explain in a moment. Second, we need to make sure that for new patients who use this model, they don't reveal their data, and their data will be kept private, which we call it private inference. What is differential privacy? In a very basic explanation, consider that a hospital take a model And there are two types of data sets. One data set D, including Alice's data, and another data set D prime that not include Alice's data. And we don't know that this hospital trained this model on which of these data sets. Differential privacy says that if the hospital published this model, then there should be a bound on the possibility to recognize whether this data set is trained on D or D prime. And there are a method called DPSGD, which you can use to train a deep neural network with differential privacy. So the implementation that we've done is like this, that we initialize a model, we propagate this model through hospitals, and each hospital train this model with DPSGD. And then this model is aggregated in a secure way such that just the sum aggregated model will be revealed to the public. And we can repeat this until we reach a convergence. So doing so in this implementation, we do not need to even trust the server. And that's a reason that why we use secure aggregation, because hospitals do not need even to trust the server. And the second motivation is that doing so, we can achieve a better accuracy while keeping the same level of privacy. I explain it. Don't worry about the formula. Just consider that you have a private computation, and differential privacy says that if you want epsilon differential privacy, you should add a noise of this variance. Then you can publish your result. If we do this in a secure way and just release the aggregated, we have shown in the submitted report that you can have this K in the denominator of the noise. So you can add less amount of noise while achieving the same level of privacy. So we can get better accuracy. This is the algorithm. I just keep it for the Q&A session. And we evaluated the proposed solution on a diabetic retinopathy data set that include 5 classes. And we used as deep neural network the SqueezeNet, which is a state-of-the-art neural net, 50 times fewer parameters than famous AlexNet. And we simulated this with this data set because we didn't have access to a larger data set. Medical data are not available. We had this simulation with 10 hospitals and other hyperparameters. The result shows that in comparison to other baselines, for example, centralized baselines 1 and 3 here, which are not in practice possible, as we explained, we cannot collect data in one place. And also in comparison to a federated learning scenario without considering any privacy, a federated learning scenario that just consider accuracy, we could achieve a better trade-off. The only practical and acceptable solution is federated learning with parallel differential privacy, which we see here that we not only achieve a better accuracy, but also a better privacy in comparison to this accepted and practical alternative. We also provided an app that a patient can take his image and make a diagnosis out of his image. Notice that we do this in a way that we don't publish the patient's data, but the model will be sent to the user's device. And because the model is trained with differential privacy, it doesn't leak information. Thank you very much.
Thank you so much for the presentation. Right now we go to Q&A. So over to you, Vishnu.
Thank you. I want to first check with the judges if any of the judges have questions. Okay, meanwhile, please go ahead.
Yeah, while I think I just wanted to finish on time to respect the timing, I just wanted to say that the contributions of our work is that we open source all the framework, and we are not based on our knowledge. We are not aware of any open source library that do federated learning with DPSGD in such a way that we could achieve like acceptable privacy and utility on the medical data. And we also are the first that use momentum in federated SGD. As you know, in optimizing neural networks, using momentum like momentum with SGD or Adam optimizer are a state of the art. So using momentum give us a better accuracy and a stable training. And we have shown in the report that how we can use this method while satisfying the privacy that we needed. And we also provided the best among other alternatives that we've shown a good privacy. For sure, there are some things in progress at the moment that we are working on, like implementing the end-to-end aggregation with homomorphic encryption, and also for private inference, we also working on to see how we can also keep the model private. At the moment, model is trained with differential privacy, but we published it. There are some methods to keep also the model private.
Thank you, Mohammed.
These are, yeah.
Okay, thank you. Questions with these backgrounds for Mohammed. Anybody, any of the judges first, please? Nakao Sensei, please.
Yes, thank you for your interesting work, presenting your interesting work. My question is about, so is there any real application case here? Like, it's a good result that is shown, and privacy preserving machine learning. I'm sure it has lots of application in the medical area, but is it really put in practice? Like, as a medical doctors looking into this application? That's my first question. And the second question is that, is there any other application area? I'm asking about the practicality of this method. Is there any other application area you are looking into other than a medical application?
Yeah, for sure. Thank you for the question. So the first application, like the main motivation of the challenge, was to propose a solution that we can use for undeveloped or like places that don't have access to the doctors. And by this progress in communication, I think what we need is that like we will approaching to good communication networks, good devices, but what we don't achieve has having access to good expert. So the main application here will be that if we could have such a well-trained model, then publishing this well-trained model to the world, then the rest is just the matter of how we can, for example, run such neural network on a patient device, for example. So that I think like it's possible for sure. The training process, this training procedure that we need to like do multiple round of sending model to the hospitals and collecting model and doing secure aggregation is highly complex and need really a large amount of time for sure. But because this is happening once, and because hospitals have data, and this is the only way that we can satisfy legal constraint and also satisfy privacy, So maybe it is acceptable to one time, let's say, suffer such complexity, but train a very well accurate model and then host it for the rest of time. We can host this model on a server and do prediction on the user's devices.
So I think I understand your point, but my question is that is the real like hospital or healthcare service agency, are they trying to use your solution right now? I'd like to know if it is used in the real world use case. If you have some experience.
Yeah, in real world use case, there was a startup that they claim that they are hosting a well-trained model for skin cancer diagnosis, and this model but the problem, I'm sure that the problem with that startup was that the model was trained after collecting data in one place, and they didn't do the privacy constraint. They didn't satisfy, so it didn't go successful. To satisfy this constraint, at the moment, I'm not aware of any successful company doing this, but it's in the vision to do that. Yeah.
Okay, thank you. I understand.
Thank you very much.
Thank you, Sensei. It's quite interesting discussion. In fact, I have several points to discuss about privacy, about how you measure privacy, about overheads of sending models, and also about ITU's focus group on AI for health. But unfortunately, we are out of time. We can discuss offline. Thomas is here.
For sure.
Back to you,
For
Thomas,
sure.
and thanks, Mohammed. Yes.
Thank you very much. We are happy to please reach us by email or any sort of question that you have. We are very happy to answer. Thank you.
Thank you so much for the presentation. Now we will go to the program after break, which is Graph Neural Networking Challenge. The first to present is Tim Steredek. Please, you can start your presentation.
Perfect. So hello, everyone. I'm Loïc Fogno. I'm currently a PhD student in Untitled Chapter and in the University of Rennes. And I represent our proposal for the Graph Neural Network Challenge organized by the Barcelona Neural Networking Center. So the goal of this challenge is to build a neural network model that takes as input arbitrary network topology, along with information about path traffic, link capacities, and nodes quality of service policies. So basically, the goal of the neural network model is to predict the average delay over each path. And by path, I mean every pair of nodes. So this has a number of applications, for instance, in optimization of software-defined networks, and also in 5G networks. So this has been isolated as a use case, for instance, when we want to optimize the quality of experience without having to resort to costly network simulation. So the organizer of this challenge proposed a RootNet baseline. So this is basically a graph neural network message passing model. And the RootNet model models hidden states of path and links and tries to converge to fixed value for the hidden states of path and links. The main problem with the approach is that the model does not take into account the quality of service policies for each node. So we need a way to add this in the baseline. So what we propose is to add the node hidden states within the RootNet model. And to do this, we transform the network topologies that are provided as input into three bipartite graphs. So let's take as an example this very basic network topology with 3 nodes A, B, and C, and 4 links 1, 2, 3, 4. What we do is that we create 3 bipartite graphs. So the first one is a bipartite graph that models relations between path and links. The second one between links and nodes, and finally the third one from path to nodes. So for instance, here, if we look at the path B to C, which uses the links 2 and 3, you can see on the corresponding party graph that you have the path B to C and the links 2 and 3. So these bipartite graphs are useful to model dependencies between path, nodes, and links, because when we want to update, for instance, the path B to C, we know that we need to look at the links 3 and 2. And conversely, if we want to update the hidden state of the link number 3, we know that we need to look at the path A to C and B to C. So this is the basic idea of our modelization. And now I will explain how we update the hidden state during training and during inference. So first, we initialize the hidden states for path, links, and nodes. For instance, for path, we input the traffic information and the time of service for each path. For links, we input the capacities of each link, and for nodes, we input the quality of service policies. Once it's done, we can start propagating the information and the dependencies between path, links, and nodes. And first, we update the links hidden state based on the path hidden state. So to do this, we apply a graph convolutional operation, which is basically based on the first bipartite graph I presented in the last slide. So this is so the basic idea is that we use a neural network to transform the path hidden states and then aggregate the different path hidden states into links hidden states. I will not dive into the details, but this is a quite classic approach in graph convolutional networks. Once we have updated the links hidden state based on the corresponding path hidden state, we continue the propagation and update the nodes hidden state based on the links hidden states. So this uses the second bipartite graph we created earlier, and then we go back to the links hidden state using the node hidden state, using the same bipartite graph in the reverse order, and we continue to go back to the path hidden state. So at this point, we have updated the path, links, and node hidden states, and we loop these operations t times just to be sure that we converge to a consistent values for hidden states. Once it's done, we update the path hidden state based on the node hidden states using the final bipartite graph. And for this special aggregation with a recurrent neural network, which leverage the knowledge of the ordering of the nodes within each path. Finally, we want to extract the information from the hidden state to predict average delays for each path. So we apply a set of fully connected layers to read out the final delay. So we propose also several optimization. I will not go into the details, but we also propose specific aggregations for the hidden states, a custom loss function, and specific policies for the learning rate. Okay, so I hope I have time for a short demo of our model. So on the for the left, on the left side, you have a simple topology with 4 nodes and 4 links. And on the right, you have the predicted path delay between each pair of nodes. So for instance, if I take the path from node 4 to node 1, the model predicted an average latency of 0.16 time units. What I can do, for instance, is decrease the path traffic, for instance, to 1000. And I see that immediately the average latency over this path decreased. And we also see that the average latency over this path decreased a bit. And this is normal because both paths use the same link. I can also change the link characteristics. So for instance, if I increase the link for capacity to 100K, then we see that average latency decrease for a number of paths that all use link number 4. So in this case, this is quite expected, but we can also look at more complex topology. So for instance, a géant topology with 24 nodes. In this case, we have more complex interdependencies between nodes, path, and links. And for instance, in this path from node 24 to node number 3, we see that we have a latency of over 3 seconds. So what we can do is maybe decrease or increase the capacity of this link from 5 to 8. And we see that we managed to reduce the latency over the selected path. But immediately we see that there are other effects in the overall network with decrease in latency in green and increase in latency in red. So this has been predicted in less than 1 second thanks to our model, which is not possible using a simulator. And we see immediately that there are very complex dependencies between path, links, and nodes. Okay, so this concludes my presentation. So for the challenge, we proposed a new graph modelization for the specific challenge using node hidden state as a baseline. We also propose a custom strategy for hidden state aggregation, and we have also more optimization in our report. So all these proposals allowed us to obtain the first rank in the GNN challenge. We have a demo available online, so you can check it out if you want to test a different configuration, and the source code is available upon request. So thank you for your attention. I will be happy to take any question.
Merci beaucoup. Thank you so much. I want to ask judges for any questions if they have, please.
Yes, this is Albert Cabellos. Thanks for your presentation. I think it was very clear. I'm curious because you came up with a very novel and interesting design for the problem. And it is very clear from your solution that you truly understood the underlying mechanism of networking in order to design it. It was not a data-driven solution, but let's say networking-driven solution. And I was wondering, how many iterations did you have to go until you reached this one, the one that you presented, which performed very well?
Okay. So it was clear from the beginning that we needed to include the nodes hidden state in the model. So if I go back to this slide, so we first added this node hidden state, and then the first iteration was just the arrows on the top, basically, where we just using the path, links, and nodes to converge to a first solution, which was not really good. So we added multiple loops to increase the performance, and finally we added this last recurrent neural network relation. So yeah, maybe 3 or 4 iterations before obtaining this final model.
Thank you. Very cool. Thanks.
You're welcome.
Jose, would you like to ask your question?
Hello all. So I just had a curiosity. So I guess that during the design of the model, you started by using standard aggregation functions like the sum. So I could see that finally you used in your report a concatenation of the average, the sum, the mean, the minimum, the maximum, and the variance. So could you tell me to what extent did it improve the accuracy of the model approximately? So it was an important improvement or just marginal?
So from what I recall, it was not a really critical improvement. The most important improvement was due to changing the learning rate scheduler. But changing the aggregation allowed us to improve by a few percent or a few tenths of percent in the final score. Basically, what we wanted to have is a model that was the most generic possible, and by including both the addition and the average was I would say the most significant improvement. And then we added the mean, max, and variance just to be sure that we didn't miss anything.
Okay. Okay, I think this is a very important point in graph neural networks in general, and it's now being investigated in depth in the AI field. Yeah. So also I could see that you had an analysis on the visualization of the paths hitting states, which I think it's quite interesting. Probably I didn't see an analysis like this in previous experiments of GNNs. So I think that it's quite clarifying the representation with T, S, and E. Also, I don't know if you made some analysis on, for example, to analyze the specific features of the path where you got less accuracy. Like, for example, to identify the generalization capabilities of the model and what kind of paths are more difficult to be modeled by your specific GNN architecture.
Yeah, that's one thing we didn't look at the moment, but yeah, definitely we know that some links, some paths are really poor predictions in some case, and from what I observed, it's mostly for complex paths with a large number of links. But sometimes it's quite difficult to understand why it's not predicting the good value. But yes, we need to look at this in detail.
Yeah, I think it's a very good path to improve and understand, have a better understanding of how it works internally. But yes, it's a good starting point having this kind of representations and this analysis. Yep. So thank you very much.
You're welcome.
Thank you, Jose. Anybody else who has questions? Any judges who would like to clarify the solution? Nakaf-sensei, please.
Yes, I have a question about a complexity, computational complexity, because graph neural network tends to consume a lot of computational power. Can you show us the rough idea of what's the computational complexity of your neural network?
Well, it's hard to compare. What I can say for sure that it's more complex than a classic approach in neural networks. For instance, convolutional neural networks with the same number of parameters would be very more efficient. In our case, we did not optimize anything, so this is a quite slow approach, I would say, but we still managed to infer the path in less than 1 second. So I believe that's still acceptable for this solution. And for the training, our best model took approximately 1 week to train. So that's a lot on 1 GPU, but we believe we can still optimize a lot on this side.
Okay. I don't want to criticize, your approach, because we know that the GNN takes, a lot of computational power. But just to know what's the, what kind of stage are you at for optimizing a GNN? So application takes just 1 sec, but training takes 1 week. That's a lot of, long time. But as long as our application time is acceptable, like 1 sec, so then we can you can probably work on optimization in the training side in future. Yeah, thanks for clarification.
Welcome.
Thank you, Nakaf-sensei. And also we have questions in the chat. I also want to ask you that about whether the hidden states can be dynamically changed. Maybe we can take it to the chat, no problem. I heard the bell now and we should switch over. So thank you so much for the great presentation and patiently answering all the questions. Back to you, Thomas.
Right now, I'm going to give the floor to the next presenter, which is Gradient Ascent. Please, you can start the presentation. Yes.
Okay, so my name is Henrike Wissing. I am presenting my team's solution for the graph neural network challenge. So, right, we are working at Fraunhofer Heinrich Hertz Institute in Berlin, Germany. So to motivate the whole endeavor, the prime use case for this is QoS and quality of experience predictions for increasingly complex networks. So in modern networks, we have normally the separation between data plane and control plane, where the data plane is responsible to provide some means of network telemetry that provides data about the current network state to the control plane, which in turn analyzes this data and then performs some optimization of the network configuration in order to meet service level agreement requirements and so forth. One way to accomplish this is to implement so-called what-if schemes, meaning that one is trying to find a function of some sort that takes the network state as an input and from that is capable to predict the key performance indicators of the network state. So the network state can be characterized by topology, routing schemes, traffic features, or features of the links or nodes. In this particular challenge, we were asked to predict the latencies, more specifically the per path packet delays. So the function in our challenge, as the name says, is a graph neural network, which has actually been implemented by the challenge's hosts. And yeah, so they have implemented various flavors and have published a great deal about what they have accomplished. And I think this is really state of the art in this field. And yeah, so we have taken this as a basis for our work in this challenge. So the input data for the graph neural network for this challenge comes from simulated data. The network simulations were also provided with a problem statement with the host, and the characterization of the network state that we could extract from the simulation was for one thing the topology of the network, of course, and then the set of paths that are routed through the network, which consists of sets of sequences of consecutive links in the network. Each link has also a certain set of features. Here we have used the capacity of each individual link, then the scheduling policy of the node at the transmitting end of the link, and the weight profile that goes with the type of service of the flow through the path. So, and for each path, we have used the average bandwidth in the path, the type of service of the flow, the average packet size in the flow, and the packet rate. As long as this was not given, we have transformed these features. We have mapped these features to floating point numbers of order of 1 to ensure numerical stability. And then we have embedded the features into higher dimensional feature vectors, the so-called hidden states. And these hidden states were fed into the RouteNet model. a sketch of the architecture as shown here. It was taken from our host's GitHub page. And for the details of the architecture, I would like to refer you to the references. Since we really did not change the architecture at all. So basically the RouteNet consists of this recurrent part of the network where message passing steps are iterated. And then at the end here is a readout dense neural network, which then yields the prediction for the pair path delay in our case. So the hyperparameters that we have tuned are shown here in yellow. There are more hyperparameters to the model, but these are the ones that we have changed. So there's, for one thing, the dimensionality of the link and path hidden states. Then we have changed the number of cycles that are performed in the recurrent part of the network, and this we have actually reduced. I mean, so in the message passing is actually the most computationally intensive part, and we have actually, so the original RouteNet used 8 iteration cycles, and we found that 4 iterations are actually just as good, or in some cases even better. Then we have played with the, we have tinkered with the parameters of the final readout dense layers, where we have increased the number of nodes in the readout layers, as well as the L2 regularization parameters. So, and here's what we found. On the in the table here on the right, you see the 5 hyperparameters that we have tuned, and each row corresponds to one set of hyperparameters that we have used. In the plot on the left, you see the loss function that we have minimized. In this case, this was the mean relative error of the predicted pair path delay. And you see this over the course of the learning. So on the horizontal axis, there are the steps of the learning process. So we have terminated at 1.2 million training steps. So in the first iteration, we took all the feature vectors that I've previously shown, and we ran this with a set of hyperparameters that was previously used by the other RouteNet publications. And with this, we got an accuracy, a prediction accuracy of roughly 25% on the test data set. And then, so yeah, so we saw that the training converged nicely, and but we are far from a good accuracy. So we, with the additional information compared to the original RouteNet, we started with blowing up the dimensionality of the network, and we started with doubling the number of readout nodes, which only gave us an improvement of 3% in the accuracy. Iterations where we doubled the dimensionality of the link and path hidden states simultaneously. And this gave us another 10% in accuracy. But then we saw, okay, we have blown up the dimensionality by a great bit, but we are still very far from overtraining, obviously, because the loss function on the test set is still like saturating. So it's not getting worse. So then you thought, okay, we are still doing L2 regularization, and if we're not overtraining, we possibly don't need that much regularization. So we just dropped the L2 regularization in the first 2 dense layers of the readout network, and this really improved it substantially again. and we ended up with a prediction error of 7% on the test data set. And this was actually the solution that we had submitted. It performs even slightly better on the evaluation data set that had not been seen before. So we end up with an accuracy of 5% on the evaluation set. And then even, I mean, after submission, we actually did another iteration with still blowing up the dimensionality and doubling the path and link hidden states. And we see, okay, so this gives some improvement, but I think, yeah, I mean, our conclusion is that the next step would be to improve the network architecture, what actually the other two teams have done, but this is how far we got with this. That's it.
Thank you so much for the presentation. Right now, we are going to the Q&A. So over to you, Vishnu.
Thank you. Yeah, Enrique, I think this is really complementary to the other presentations. So it is quite interesting. The approach seems to be quite complementary, and this completes, at least personally, I think my sphere of knowledge. But I want to ask the judges if there are questions for Enrique, please.
Yeah, hello, this is Albert Cabellos. Thanks for your presentation. And I very much agree with Vishnu's comment. I think that this is a very complementary presentation to the previous one, because the previous one was trying to solve the challenge by designing a new solution. And here you try to solve the challenge by using very sophisticated machine learning techniques, and this shows a lot of knowledge from your side. I was wondering, which of those hyperparameters do you think that was most relevant to increase the accuracy of the whole model? Or what do you think that was the turning point of your solution?
So, the thing that was kind of obvious, but what was hiding in plain sight is that going softer on the regularization still improves a lot. Yeah. And it was, it was really, we were sitting back and thinking, okay, we have blown this up by so much, and actually we should overtrain if the network should have the capacity to model the information. But then we didn't see any signs of overtraining. So we just dropped the regularization. And this was something, yeah, which was kind of obvious, but which we tried at a very late stage. So then I think apart from that, the dimensionality in the hidden states is the hyperparameter that we gained the most from. But there's another point which really surprised me actually, that we observed if we reduce the number of message passing cycles, we actually benefit. So we tried this at a very early stage, initially to reduce computing time, and at that point, the dimensionality of the network was still small. So we were working with 32 of 64 hidden states, hidden dimensions, dimensions in the hidden states, sorry. And then actually the performance was slightly worse with fewer message passing iterations, but this turned as we increased the dimensionalities, and in the end, like for the bigger networks, the 8 iterations actually performed worse than the 4 iterations, and this is something that I really can't grasp, and which came as a surprise, because I was thinking, so okay, the paths are kind of, they have more links than 4 links. They're much longer, and I was thinking, so okay, if we reduce the message passing, the information does not spread over the entire network probably. So what I'm saying is that this is something that I don't really understand, but we have observed this.
I agree.
Cycles are better than more cycles.
Yes, some of your technique seems a little counterintuitive, but I agree. They render better results, and this is something super interesting to do more research and to try to understand. So thank you very much for your presentation.
Yeah, I agree. I think the journey seems to be quite interesting here. I just want to quickly, I know we are running out of time, just quickly look at Jose's question. Jose, please.
Okay, hello again. So I have a quick question. I could see that to encode the scheduling information, the key scheduling information that originally is not in the baseline, you used numerical values. So, and this is a categorical feature. So I'm just curious if you tried to use one hot encoding vector, or what was or why did you decide to use numerical values instead of one hot encoding?
So I don't know, it was just the easiest to do. We did not try one hot encoding, although in literature, I saw that this is kind of the standard thing to do. But then I was thinking, okay, the information contained in this is just the same, and it was just the easiest to do. Sorry, I mean, it's not very academic. And so I may mention that none of us has worked with neural networks before. And at this point, I would like to thank you guys for providing such a great opportunity for us to tackle this topic. It was really great. Yeah, so sometimes we just did the easiest thing is the answer.
Okay, anyway, I think it's a valid alternative. Thank you very much.
Thank you, Jose. Thank you. We thank Enrique for the presentation. Back to you, Thomas.
Thank you so much, Vishnu. We are going straight to the last presentation in this problem statement. This is Salzburg Research.
Okay, thank you. So my name is Martin Happ from Salzburg Research, and we present now our solution for this challenge. So yeah, we've already heard enough of what the challenge is really about. So I'll go over this very briefly now. So the original RootNet model didn't really take into account the scheduling information. So it performed rather poorly when scheduling is present in a network. And the challenge was now about to incorporate scheduling in either a new model or an improved RootNet model, and then estimate their average delay per flow. So the original RootNet model consists basically of two important neural networks. One is responsible for, let's say, updating path state information, and one is responsible for updating link state information. So both are gated recurrent neural networks in the original RootNet model. And this is iterated several times, which is called as the message passing, and the final path state information is then used as an input for a readout neural network, and this estimates then the average delay per flow. And so our idea was basically some kind of combination of the first and second presentation. So we changed slightly the model and tried to optimize hyperparameters at the same time. So our first idea was, well, we now have scheduling information, and to somehow take care of this increased complexity, we decided to not use gated recurrent neural network for the path state update function, but a stacked version of it. So this is basically two recurrent neural networks that are where information is not only passed, let's say, vertically through a path, but also horizontally. So they're interchanging, let's say, information with each other. So we didn't really model the scheduling in terms of how the first presentation did it, but we let's say, the neural networks do their own magic and try to solve this problem. For the links data update function, the sort of we decided to replace it with a feed-forward neural network with 2 layers. And so then the message passing is basically the same. For the dimensionality of the hidden states, we increased it slightly to 64, as it has shown to improve the results significantly, but it didn't go above that as the computational time it takes increased rather large. So we decided to stay at 64, which is a good compromise between good results and fast calculation of the training. So, and for the readout function, we added sort of another layer, which doesn't have an activation function. So it's more or less some kind of a regression that takes place. And the path state informations are not only used as input for the first readout, but also for the second readout layer. So it's more or less something like a residual neural network or similar to that, which doesn't really improve the results very much, but it helps to make the whole network more stable. So this is just in a summary what we have done. So the main changes were stacked gated recurrent networks and a feed-forward neural network and this additional layer for the readout. So so the training, we trained until about 1.2 million steps, and we didn't really optimize with respect to learning parameters. So we observed that that with the original parameters or slightly changed parameters, the loss function or the learning rate sort of got too small very fast. So at some point, we just increased it again and then let it run again until 1.2 million steps. So, and in the end result, we got a result from the evaluation data set of about 1.94% error. And we didn't really have much time to optimize it even further. So if we, so in the current iteration of our model, we changed the links data a little bit again, and then we could achieve an error of about 1.2%. But we are very, but we think we can even get below 1% if we train it a bit longer, the model. So, and we used GForce RTX 280, and it took about 48 hours for 1.2 million steps. Okay, thank you for your attention.
So, Martin, thanks again for your presentation. I have a similar question, kind of similar question to the ones I put to the other participants. I think that the changes you made to the baseline, they are clearly the reason why you obtain better accuracy. That's obvious. But the changes, they are not obvious. How did you reach them? Because the dimensionality of the changes that you can have is huge, right? So you choose a certain amount of changes based on some intuitions. And I was wondering which was your intuitions, because that's really good intuition.
So in our team, there are several people that are well known with networking, and so we tried several ideas they had. I myself, I'm not really well versed with networks. I'm a statistician, trained statistician, so that's rather new for me. But yeah, we tried many ideas, and this one that we then handed in turned out to be the best. So
thanks. Cool. Thanks. Thank you very much.
Thank you, Albert. Any other questions for this team from the judges? If not, from any other participants, anybody else who has questions? Yeah, there is a question on the chat. Please, you can unmute and ask, please.
Thank you. So thank you for the presentation. I have just a small question out of curiosity. how did you manage to embed the node features, such as quality of service policies, into the link states?
What features are you referring to?
Yeah. I was just wondering because in the problems, if I remember correctly, the nodes features like the quality of service are specific per nodes. So how did you manage to add these node features into the link?
Right. So the type of service is a node feature, but a flow has a certain direction. So it goes from, let's say, node A to node B. So there's one link that connects these, right? And so we assigned the link that goes from node A to B, the type of service which is given by the node B.
Okay, I see. That's very
because
clear.
this node somehow handles this scheduling then.
Okay, thank you.
Actually, I want to ask if the 48 hours training time, I believe this is also quite good, I should say, when comparatively I should say. So what led you to the training time of 48 hours? Is that a choice, or is that
This was an arbitrary choice, so we just looked at the loss functions. So where here it won't change much anymore, so we just stopped at 1.2 million.
And is that one GPU? I think
that's one GPU, yes.
Okay. All right. In that case, we thank the speaker, and back to you, Thomas.
Thank you so much for handling the Q&A. Right now, we are going to a different problem statement. This is from Tuxel, using weather information for radio link failure prediction. The first team to present is Link Busters from NEC Japan.
Hello, everyone. My name is Dheeraj from NEC Corporation. I would be presenting a solution to problem statement 36, which is radio link failure prediction. For this entire presentation, radio link refers to wireless backhaul links. We use this terminology to be consistent with the original problem statement. So reliable backhaul links are essential component to realize high performance 5G communication era. However, these radio links typically use millimeter wave, which are susceptible to bad weather conditions. Our goal here is to predict radio link failure for next 5 days, given weather forecast made today. While the problem statement is fairly simple to understand, let's look at what makes this problem statement challenging, or in other words, interesting. Firstly, forecasting weather stations are not located at the same place as the radio links. Also, even for forecast, it may result in different impact at different times, say due to different wind flow directions. So our challenge is to account for these spatial and temporal correlations between the weather forecast stations and the radio link performance. Secondly, the radio link performance does not only depend on weather, but rather a combination of multiple factors like radio configuration and even topological features. For example, a radio link is going to behave very differently if it's an open land than how it behaves in dense urban area. All this means a large feature space that needs to be considered. Lastly, since this is real data set, less than 0.5% of the data had radio link failure. From machine learning perspective, this makes it extremely challenging to predict radio link failure accurately. So before I present our solution, let's take a quick look at the existing research. Majority of the work is reactive. That is, they do something after detecting initial radio link degradation. As for the predictive methods, many papers use radar-based train echo maps, but these maps are not exactly forecast, but rather nowcast. Hence, the predictive ability is limited. We did find some patents regarding use of generic weather forecast, but they take limited features into consideration to predict the failure. Our approach mainly relies on data processing methods where we leverage on domain knowledge and then combine it with relatively simple machine learning model. In fact, they are simple random forests. So the first thing, how about we, since location of radio links and weather station are in the same, we can choose a subset of weather stations which are, say, some distance d naught apart from the target radio link. Now there is a trade-off with d naught. If we choose very large d naught, then there is very low correlation between the forecast and the radio performance. And if we choose very small d naught, then we do not capture sufficient information for radio link prediction. To overcome this problem, we create some graph-like structure where we rank weather station based on the number of edges a weather station is from the radio link. To choose the actual value of this D, how we connect the graph, we look at two things. First, effective distance, and second, homological persistence. So by effect, as mentioned previously, some same forecast may result in different impact at different times due to wind flow patterns. So we scale the distance between nodes based on the wind speed and direction, such that distance between nodes increases if wind is blowing away and decreases if wind is blowing towards. Secondly, to find what is a good value of perception distance D, we look at how graph would evolve for all possible values of D. As the value of D increases, different spatial features are generated till the entire graph is fully connected. We choose the value of D such that most stable feature is preserved. Stability here intuitively means that even if we perturb the locations of the node slightly, the features are still retained. This stability is formally known as homological persistence. Next, we simply integrate all this information. We concatenate all the features, that is radio configuration, topology related features, and weather forecast along with the weather station rank. And these data samples are then used to train the our machine learning model. Looking at the features themselves, as mentioned before, we have large number of categorical and numerical variables. Some of them are shown here, like the forecast itself, like scattered cloud, heavy rain, and so on. The traditional approach is to use one-hot encoding, which simply blows up the features dimensionality, which is already very large. So instead, we decompose these categorical variables into multiple meaningful binary variables. An example is shown here. The same approach is used for other variables as well. This binary decomposition is followed by iterative feature reduction. Since we use decision tree-based classifier, we can rank the features based on importance and then remove the least important feature. This process is carried out till we observe some drop in F1 score by a certain threshold. Lastly, for the imbalanced data set, we overcome this problem by generating synthetic minority class data samples using a technique called SMOT. This is followed by random undersampling of majority class to achieve a relatively balanced data set. Coming to the machine learning model itself, we used actually an ensemble of decision tree-based classifiers. Why we chose a decision tree-based classifier in the first place is mainly because of practical reasons, low computational complexity, not just prediction, but probability of failure. This gives us some associated confidence level and ability to even interpret a prediction. Just to summarize, we had the problem of spatial and temporal correlation. We solved this by using graph-based weather station ranking. We had the problem of high feature space dimensionality. We did binary decomposition and feature reduction. We had highly imbalanced data set. We did some rebalancing. As for the evaluation, we achieved 0.78 on F1 score for 1 day ahead prediction. To compare it, what we did is, since there are 3 elements, we just remove 1 element at a time and see how much extra we can get. So if we do not consider the graph thing, we get lower precision. Without feature decomposition, basically there is no learning, and without rebalancing, we get better precision, but at the cost of lower recall. So as for the contribution, we presented a method to predict radio link failure using weather forecast data, and we tried our best to keep it as much practical as possible. Thank you. So if you have any questions, comments, or suggestions, they are welcome.
Thank you so much for the presentation. Now we go to Q&A. Over to you, Vishnu.
Thank you. Thank you, Dheeraj. I think it was a very clear presentation. I also want to say that this data set is not simple. I mean, it is taken from real network, and Tuxal has kindly donated it. So I think the approach is quite interesting. I want to ask judges if they have any questions. I have several comments, but I think we should ask the judges if they have any comments. Meanwhile, while I wait, I want to go to slide 14, Dheeraj, if you don't mind. I think
Yeah,
I
sure.
had some. Yes. So, yeah. So this was a problem in the data set. I mean, it is not a problem; it's a feature, I should say, in the data set that failures were rare. These are rare events. Yes, we understand. What exactly is the approach that you have taken here? Could you and how did it help at all? Did you compare this without balancing with balancing and see what happens?
So we compared it here. So for the proposed method, that is with balancing and keeping everything else the same without rebalancing the data set. So we actually observed the same F1 score. There was some drop in precision, but there was drop in recall, but the precision rose. Our focus was mainly on recall because the cost of a failure is more than not predicting a having a false positive. So we focused on recalls, but to be honest, working on this data set, having this rebalancing or creating this artificial sample did provide us some means to control false positives or false negative, but not actually improve the F1 score, not improve the prediction.
So let me come back to this in a bit. So you mentioned in the beginning that this problem statement is for point-to-point links. I think your point is that it is point-to-point. So I want to ask, why is it important? I think you mentioned about pattern. You mentioned about the distance d that you mentioned. You showed us. Is it really a problem if the nodes move? That's my question. So I understand your D will change considerably if the nodes move, but the fact that they are stationary and they are point to point, is that really important? Could you comment?
So firstly, accuracy, we should keep in mind that we are trying to predict radio link failure based on weather forecast, which itself is an estimate, right? So we do not know the weather forecast. We don't even know the weather forecast at the location of the radio link. So if we add too much noise into the system, then we empirically also observe that the performance of the model sharply decreases. So in that sense, we want to be very selective with what kind of weather forecast we use to predict the target. Will there be a failure at the target location or not? So next, as for the point-to-point question, it's not necessarily point-to-point. One node can be connected to multiple other nodes. So I didn't really get what do you mean by point-to-point.
Well, it is the same thing. I mean, they don't change at all. Their locations don't change at all. That's what I mean. It is basically that these links are point to point. I mean, they are connected between fixed entities.
Okay.
Yeah.
So for this aspect, how a given weather forecast at a given location impacts the performance at the target radio link is very different based on how the wind is flowing. There may be other parameters also. So we just picked on wind as one main thing, and we observed quite a lot of improvement based on that. So we try to create this effective distances where we remap the locations of these nodes to a separate, like a new projected 2 dimensions, and then use those distances to compute radio link failure.
Thank you, Dheeraj. Any questions from judges again? I don't see any. I mean, I have several other points about, generalization and so on, but Thomas is here. And so we should take it to the chat window and we can discuss it there. Thank you once again. We thank the speaker. Over to you, Thomas.
Thanks a lot, Vishnu, and thanks to the previous speaker. Now we are going to the next presenter in the same problem statement, radio link failure prediction. Is IEC research.
Good morning, good afternoon, or good evening to everybody. My name is Juan Samuel Perez, and I am the team leader of IEC Research. We're going to be talking about our approach to the radio link failure prediction problem using weather information. The IEC Research team is formed by many professors of the Electronics and Communications Engineering degree program, in the Dominican Republic. Here's our agenda for today. We're gonna take a look briefly at the problem statement and the needs associated with it. We're going to speak about our general strategy for tackling the problem, some details about the model that we proposed, some performance metrics of that model, and then we're gonna have some final remarks and then the Q&A session. This challenge required the use of AI and/or machine learning for the prediction of future radio link failure occurrences. And the hope of the organizers was that we could create prediction models that would be able to predict from 1 up to 5 days ahead in time. Radio link failure is an anomalous condition of microwave line-of-sight links that has been defined by Turkcell. So in this sense, it is not standardized anomalous condition. It has been defined by Turkcell for this problem, and they have defined it using threshold on standardized metrics or KPI, key performance indicators. And the prediction of the early prediction, of radio link failure can result in mitigated downtime or reduced service degradation to the subscribers because upon the prediction, the telecommunications companies can, for example, dispatch engineers to the field or make contingency plans on the network side. Now, the data set that we used for this problem was directly provided by Turkcell, and it contains an anonymized information associated to some meteorological stations and to the RF links of interest. And we have there a timeline of weather forecast and measurements that includes measurements of humidity and temperature, for example, a timeline of KPIs of the RF links that includes information like the link length or the received signal level. We also have in that data set a characterization of weather stations and RF site locations. And finally, and very importantly, we have some spatial information where we were given relative distances in between the RF sites and the meteorological stations. There were some particular challenges of the data set that were mentioned before by our colleagues. We have a significantly imbalanced data set with a small percentage of RLF occurrence. So it's a very rare event, however important. And there was some uncertainty in regards to the origin of the weather predictions. And that came up in some conversations for clarification that we had with the Turkcell team. Also, there was some missing weather stations forecast data, and an interesting challenge here was the alignment of spatial and temporal data for tackling this challenge. Now, the issue of how the meteorological conditions affect radio links has been very well documented in the literature, both academic and professional. However, many of these contributions don't include maybe models that are widely available, maybe openly available, and that provide actionable information so that telecommunications companies can use them, and as our colleagues were emphasizing, that allows them to take measures in advance. Now, our strategy was very simple. We understood this problem as a binary classification task, and we envisioned a simple model, as simple as possible, that would predict the occurrence of the radio link failure per mini-link ID. And that is, in the terminology of the problem, each end node of the radio link. And we decided to use as inputs the radio link KPI history of that end node and the associated weather forecast data. Now, the assumption here was that the KPI history of the radio link would contain information concerning the susceptibility to failure or degradation of the link, while the weather forecast would provide information on the expected conditions the link would face in the immediate future. So when we built our model, we even made these assumptions even more simple. For the KPI history, we only used the previous day's data, and for the weather forecast, we only used the next day's forecast data. And this data, this forecast was the one that provided information from the closest meteorological station to the RF site of interest. And our experiments and discussions in the team then supported the use of decision tree models so that we could maximize interpretability, which was highly stressed by the organizers of the challenge. We wanted to make our model robust against feature scaling issues, and we wanted to use the embedded feature importance capability of decision tree models for achieving a dimensionality reduction. Now, here are some details about the model that we proposed. We implemented it using the decision tree classifier from scikit-learn. It had a low depth, so a good level, good generalization capability. We used class weights, very simple approach for handling the unbalanced data set. And at the end, we only required 29 input features for the prediction. And this is very relevant because many of those features were one-hot encoded, were based on categorical features. Now, the performance on the true class, which is the one that I would like to emphasize for the training data set, was about 60%. And we can see that the percentage of samples of the true class was very small. This first data set was provided by Turkcell, and it was used for the training. On the second data set provided by Turkcell, we only used it for testing, and then the predictions on the true class were lower, were about 30%. However, you can notice on the confusion matrix that the samples that we had available for that testing were the number was very reduced. Some final remarks. Our model is as good as the weather predictions. The source of the weather forecasts, their accuracy and consistency are the most important characteristics that our model exploits. And during the development, we observed better results trying to estimate directly the RLF occurrence instead of intermediate estimates of the KPI parameters upon which it is based. Thank you very much.
Thank you so much, Juan, for the presentation. Right now is Q&A session, so over to you, Vishnu.
Thank you, Thomas, and very nicely put by Johan. Well, let me ask judges first. Any of the judges, you have questions for Johan? Yes, Nakao-sensei, please.
Yes, thanks. Thank you for your presentation. I'm interested in your accuracy result. It's 0.9, and you used did you use the random forest or that's just a simple decision tree? And you consider 29 features you said, and which feature is most contributing to your accuracy, the high accuracy? Can you tell? I'm interested.
Excellent questions, thank you. So the accuracy that we obtained, the overall accuracy was about 90%, and in particular over the true class, it was about 60%. And for getting these results, we didn't use any ensemble methods. We used a very simple decision tree, as I have presented here.
Yeah.
So the most important features, as you can see, according to this model, are the forecast of thunderstorms and rain, the height of the RF site, the historical data concerning the link unavailability. Those were the features that ranked higher in our tree and were the ones that we preserved when we used the feature, the dimensionality reduction, and we kept those 29 features.
Mm-hmm. Thank you. So if you use ensemble method, would that improve even further from 90% to even more? Because the last presentation I reported like almost like 100% accuracy. And you know, if it is a simple decision tree classifier, maybe you can try random forest to increase the accuracy maybe.
Yes, that is what we expect. We expect that if we use more complex models like random forests or gradient boosted trees, maybe we would have a better performance than the one that we obtained. And maybe we could use models, we considered this in the team, we could use models that exploit the time series nature of the data set that we were provided. So maybe using recurrent neural networks could be a possibility. However, in this case, because of the expectations of the challenge, we prefer to provide a very simple, very highly interpretable model. We understood, based on discussions in our team and with the organizers of the challenge, that this was very, very important for them.
Okay, very clear. Thank you very much.
Thank you, Nakao-sensei. Any other questions from judges? I don't see any. In that case, we thank Johan for the excellent presentation, and back to you, Thomas.
Thanks a lot, Vishnu. Right now, we are going to the next presentation. This is on traffic recognition and forecasting. This was a problem statement from our colleague from St. Petersburg University of Telecommunications. The team that is going to present is Usatu.
Good afternoon, dear colleagues. My name is Alexei. I'm glad to present you the results of our work within the challenge. The theme of my speech is traffic recognition and long-term traffic forecasting based on artificial intelligence algorithms and metadata. 5G IMT 2020 technologies are a natural stage in the development of a mobile network. To achieve the established by the ITUR primary indicators of network performance, it is necessary to revise the algorithmic and software components of network protocols and architectures. According to the concept ITUR structure and general goals for the future development of IMT 2020 and beyond, infrastructure must be based on software-defined networks and network functional virtualization for providing new quality level and service control possibility using new algorithms based on deep analysis of network functioning. The main goal that our colleagues from St. Petersburg University of Telecommunication have set for themselves is to design greener traffic-aware SDN NFV networks with efficient resource allocation to ensure good quality of service. To conduct research, they developed an experimental network architecture for generating various types of traffic. This architecture was implemented as a laboratory bench based on Department of Communication Networks and Data Transmission and allows to perform a research in the area of algorithmic and software development for SDN NFV networks. Network traffic analysis includes two main tasks that were set for our team. The first one was recognition of traffic types, traffic classification, and the second one was traffic prediction. Solving both problems will allow more flexible control of traffic flows and accordingly increase the efficiency of resource allocation of network equipment. The problem of traffic classification is the theme of many researches of different scientific teams around the world. The slide shows some publication dedicated to this. Let me not read them. The presentation is available on the site. Traditional research distinguish three main approaches to the problem of classifying network traffic. Port-based, when the type of traffic is determined by Ethernet port. Payload-based, when the decision to classify traffic is made based on the amount of traffic passing per time interval. However, the most effective and modern one is to use passive monitoring of a network device and statistic processing using machine learning. The formal statement of the problem considers the traffic pattern X that has passed over the time interval as a vector consisting of two components, features, the number of bytes and the number of packets. The set of classes contains two types of traffic, as we can see, IoT traffic and video traffic. A training sample is a tagged device monitoring statistic. It is a set of etalons, each of which is a pair, pattern and traffic type. To solve the recognition problem, we need to find a function that assigns a type of traffic for each unknown pattern. Since in the provided data set, different traffic classes are represented unevenly. At the stage of data preprocessing, we oversample the trained data set. The oversampling algorithm estimates the statistical characteristics of a class that is poorly represented in the data set and complements it by generating etalons. For the classification, we decided to use cat boost method, which implies the ensemble of a set of simple decision trees and decision making based on gradient boosting. Cat boost is a high performance open source library. As we can see here, for gradient boosting on decision trees from the leader of IT market in Russia, Yandex. The algorithm allowed us to successfully this algorithm allowed us to successfully solve the task of traffic recognition and achieve accuracy of 97%. The slide shows the confusion matrix of the results of checking the recognition algorithm on a test sample. Next task 2, network traffic prediction. The idea of using machine learning technologies for traffic prediction has also owned the researcher's mind for quite a time. There are works in which It's proposed to use recurrent neural network, long short-term memory, and convolutional neural network for traffic forecasting. However, for solving our problem, most of these methods are unapplicable since they require large training data sets. We have very short data set. The formal statement of the problem considers the number of bytes and the packets as two independent time series. Since the time grid is irregular, the time intervals vary from 3 to 19 seconds. Discretization is required. We need to transit to regular time intervals. It was decided to consider the hourly forecasting interval. As a result of solving the problem, it is necessary to find the function for each time series that taking as input information information about the previous measured traffic values returns the traffic forecast for the next hour. This corresponds to the classical nonlinear autoregressive time series model of depth n. Since network traffic is known to be self-similar, it is assumed that there is a seasonality component m. Since the original data contained outliers, the value outside the specified bounds were adjusted using neighbor values. The best forecasting results were obtained with the following autoregression parameters: depth 6 hours and seasonality 24 hours. Thus, the forecasting model receives traffic data for the last 6 hours as input, as well as traffic values at the same hour of the previous day. It's decided to use a multi-layer perceptron as a predictive model. The slide shows its architecture. The number of neurons on the hidden layer was experimentally selected 15. The selected network architecture made it possible to achieve the following metrics on the test sample. For bytes prediction, we use SGD optimizer with learning rate, such as on the slide. And for packets, we used Adagrat optimizer. Here you can see all our results collected on one slide. We believe they allow us to conclude that both tasks have been successfully solved. We are pleased to note that when solving the forecasting problem, the training sample consists of only 200 etalons, a little over 8 days. With a lot of statistic, we could include another component of seasonality in the model, weekly. This would significantly improve the accuracy of the forecast. Our team consists of third, fourth, and fifth year students studying in the specialty special organization technical systems at the Department of Computer Science in Ufa State Aviation Technical University. Here it me. Thank you for your attention.
Excellent presentation. Before I hand over to the judges, I want to ask, are these are undergrad students, the third year, fourth year, fifth year? What type of students they are?
It's future specialists.
As in, is it a 4-year program, 5-year program?
5-year program. We study at according to 5-year program on our department, and students of the team.
Thank you. Can I invite judges for any questions? While we wait, Alexei, would you please tell us which application or which or what all different types of application have you used for evaluating this model? Did you use any specific application, or is that not a criteria here in your evaluation of model, please?
We developed our own program based on well-known libraries such as TensorFlow and Pandas for prediction, and for traffic recognition we used library CatBoost.
No, what I want to ask is the data where includes packets from what type of application?
The data set we get from our colleagues from SUT, St. Petersburg University of Telecommunication. They generated them from such experimental network. As you can see, here is an example of statistic that they gave to us.
I see that it is IoT and video. Yes, that answers my question. Yeah. Yes, thank you.
Only IoT and video.
Yes, thank you for that. And yes, our colleagues in St. Petersburg University are great collaborators. We work closely with them. Once again, call for judges. Any questions from the judges? Clarifications? While we wait, I also want to ask, you are analyzing network traffic data, for example, video, IoT, etc., etc. So some of the judges may ask about privacy and private data privacy. What would be your answer?
A question of privacy, we don't consider the privacy problems and other because we worked with synthetical data set, and our research was quite theoretical. We try to build predictive and recognition models, and we try to understand the complexity of recognition and prediction algorithms. So the results was that multi-layer perceptron, simple, can solve the problem very, very good, as we can see here.
Thank you.
Did I
Thank you.
ask the question?
Yeah, thank you. I also think that you're not looking inside the packet. I think this is not looking in the payload. It is, yeah, right?
Yeah, yes. We don't analyze what is the packet contains. It is a passive observation on the data plane, only on the data plane, because colleagues perform the research in area of SDN and NFV. So the main goal is to perform a prediction only based on raw data.
Okay, we thank Alexei for the presentation, and back to you, Thomas.
Thank you so much, Vishnu. And thanks, Alexei, for the presentation. Now we are going to a different problem statement. Of course, it's last but not the least. This is channel estimation, machine learning applied to the physical layer of millimeter wave MIMO systems that was hosted by North Carolina State University. So the first team is ML Dojo.
Hi, I'm John Palacios, and I'm going to present Learning to Detect on-site specific channel estimation with hybrid MIMO architectures. The problem we have is the following one. We have two devices that are communicating, and each of them has multiple antenna elements. Between these antenna elements, per each frequency, we have a channel that goes from each of the antennas. Then multiple measurements using different beam patterns are taken, and our objective is to turn these measurements into a channel estimation. Luckily for us, the channel we are dealing with is a geometric channel, which means that we can decompose the channel into its different path contributions. Each of these path contributions looks as follows. First, there are four properties: the angle of departure, angle of arrival, time of arrival, and complex gain. You can find the expression of the path contribution per frequency on the bottom right of the slide. The important take from this expression is that the matrix that's created, it's rank efficient with rank equal 1, and it's a known expression from the parameters. So the formulation we get is this one. We have the measurements related to the channel and the beam patterns, and the channel per frequency. Now, these are multiple values for input and output, and the first thing we like to do is to rearrange them, group them into a single piece, right? Into a single matrix. So they are rearranged and merged in order to be single variables. And there are more details about this in the report, but it ends looking something like this, right? We have the measurements defined as for the channel matrix and a whole channel matrix for all frequencies. Now, the objective is simpler. We don't have multiple elements. We simply want to transform the measurements into the reliable channel matrix, right? So we go for the maximum likelihood approach. We see this one is equivalent to a best matching projection problem. And as such, we aim to solve it by using a custom machine pursuit algorithm. This is an iterative algorithm in which at each step, we solve the best projection problem in order to extract a path. So our solution looks as follows. We start by initializing the residual measurement matrix to the measurement matrix. And while there is a path detected in the residual measurement matrix, we extract its components, then recompute all paths' complex gains values by linear MMSE. And then we proceed to update the residual by subtracting all the estimated paths contribution to the measurements. After there are no more paths to be detected, we use all path components together with alpha, their complex gains, in order to reconstruct the channel. Our novelty or contribution is the way we detect and the way we extract. Our detection is by null hypothesis contrast with a confidence gamma. So our null hypothesis is that the measurements are noise. Under this assumption, the following expression on the top left between absolute value follows a Rayleigh distribution with a known parameter sigma. That means that we have an expression for both the median and the gamma percentile, which we are interested in. Together, with these two parameters together, we can create a confidence checking expression, right? Where whenever this expression in the bottom left is not satisfied, we can say that we have detected a path, right? Then for the extraction, we use a cutting plane optimization approach, in which we start by retrieving the estimation from the detection. We have to evaluate different triads of parameters. And then in an iterative way, we proceed to estimate by grid search, first the angle corresponding to the device with the largest number of antennas, then the other angle, and finally the time delay, tau. As for the learning, we have to know that our solution is an iterative algorithm in which gamma, the parameter we are seeking to learn, only matters for the detection. That being said, what's going to happen is that if we modify gamma, unless we go up to a given threshold in which the null hypothesis condition is met, the output is going to be static, right? In other words, the error function with respect to gamma is going to be a function that only changes in those static thresholds. It's going to be a step function. So what we do is we run the solution using a lower bound gamma minimum, and also take note of the required gammas for the threshold to be triggered together with the resulting error. Then we reconstruct the error step function, merge the error step functions into of different runs, and finally, once we have the full step function reconstructed, we select the gamma that minimizes the error. For the training set, we are using only 50 samples out of the 10,000 that are available. Our training is done on a simple CPU with no GPU required. One advantage that our training method has is that instead of being iterative, it's analytical, which means that it will always lead to the optimal solution for a gamma. On the right-hand side of the slide, you can see the results of the training for the different data sets together with their training times. By having a proper analysis of the problem, we managed to improve the model's accuracy and robustness, reduce the model's complexity, improve the training method, increase the training accuracy, and reduce the training time. Thank you for attending this presentation, and I'll be pleased to ask any question answer.
Thanks a lot, John. Now it's time for Q&A, so over to you, Vishnu.
Thank you, and thank you, Joanne. Can I please ask if any of the judges?
Yeah, could you scroll up for the slides? One slide.
Sure. Which one do you want me to go to?
So you, as you mentioned, you use 50 samples out of 100, if I remember correctly. That page.
Out of 10,000, yeah.
Yeah. So I'd like to know the criteria you choose the training set.
Oh, it was complete. Yeah, it was completely.
And my second question is why no GPU is required for the training process? Thank you.
Oh yeah, the method for training we design is so simple that it doesn't require one. We simply didn't use a GPU, simply run everything in a CPU, and as you can see, the largest training time for dataset 3 is slightly over 3 minutes.
I'm the other team member. So this is, we chose to do a method that is like this, so that whenever you move to a different scenario, and that's important since like it's important to also estimate a channel whenever your channel is changing over time, then you don't need to retrain on a large set, but rather on a very small, and it doesn't take long.
Exactly. We made as much analysis as possible in order to reduce the method's complexity, such that the training would be just, you want to deploy in a new area, you just train 50 samples, you wait for 1-2 minutes, and you have it. Train and with the best gamma value.
John, you were about to answer the first question of Mr. Ming. So could you, or did you answer his first question?
The first question was how we selected the 50 samples, right?
Yeah.
Sorry, I think I was on the way. Yeah, it was at random. So I think they are shuffled randomly in the data set already. We simply selected like there was a script providing in order to generate samples in which you can just type the number. We put there 50 and we got 50 samples. We use them for training.
So these are data sets which were provided by the host, right?
By the competition, exactly.
Okay. Okay. Very good. Very good. Okay. So maybe Joanne or Dolores, if you think that the data set itself was, did you make any changes to the data set? Because we discussed during some of our roundtable discussions, I remember we had some questions around the data set. Is that all clear? Did you had everything that you were looking for?
We were actually the ones that spotted the small typo in the dataset creation, in which the channel was set to be flat in time. So it was equal. It was being replicated in the different frequencies.
That was the problem with the MATLAB script, if I remember right.
Yeah, but it was
okay.
corrected, and we updated the.
Okay, sounds good. Sounds good. All right.
The test was not run by us, so we have to upload the solutions and then the tests.
Okay.
Yeah.
In that case, I don't see further questions. We thank Joanne and Dolores, and thank you so much. Back to you, Thomas.
Thank you. Thank you for having us.
Thank you so much for the presentation. Now we are going to the second presentation in this problem statement. We have Team Icarus. This is from Linköping University and Lund University.
I'm Özlem and postdoc at Linköping University, and other team members are from different universities in Sweden, and we are all funded by the project, VAS project, Wallenberg Autonomous Systems and Software program. And again, we consider the same site-specific hybrid MIMO channel estimation problem. Let's briefly go over the system model and also challenge description. We have a multiple input, multiple output system and frequency selective channel, hybrid millimeter wave channel, and there are more than one subcarrier, so there are multiple subcarriers, and there is a channel matrix here. It's each subcarrier, so our aim is to estimate these channel matrices, frequency domain channel matrices at each subcarrier. So these are the system parameters, but the main thing is that we are provided a training data set collected from the realistic data sets by ray tracing. And during offline training, the amount of channels is this. Both true channels and received noisy pilot sequences are available in frequency domain at different signal to noise ratios. In testing stage, we only know the SNR range. There are 3 different SNR ranges, not exact SNR. And also we consider different problems corresponding to different received pilot sequence length. So again, let's briefly go over the system model as my colleague already described it. He actually described starting from the frequency domain channel, but by looking at from the time domain perspective, there are multiple delay taps, and here capital L is a tap length, and L delay tap of the channel in time domain can be written in this form. And these matrices AR and AT, the details can be found in the report, and are for the array response vectors, for the receive and transmit array response vectors, and their columns correspond to that for the uniform linear array. And we have a diagonal matrix with complex path gains, and all the other system parameters like pulse shaping and sampling time are incorporated into these diagonal complex elements, also path loss. So there are an important thing, because true channels are available in the data set. So also based on our observations by observing the channel data sets, we can use this extended virtual channel model. And there are two types of sparsity. This sparsity exists in the site-specific channels, but also from the theory in millimeter wave channels, this sparsity exists. First of all, time domain sparsity. And actually, this number of non-zero taps is much smaller than L. And we can use this information in order to improve the signal-to-noise ratio. Because in time domain, some received signals will only contain noise. Another sparsity that we can explore is the spatial domain sparsity, because its characteristics of millimeter wave propagation, and each non-zero tap only contains beams from a small number of angles. So we can actually use some grid for angle of arrivals and angle of departures here, GR and GT corresponding grid sizes. So these are again a sparse matrix, but it's a full matrix. So this is the extended virtual channel model. And the frequency domain channel can be written in this form. And we see that after applying discrete Fourier transform, the sparsity is preserved. So also the same sparsity pattern in time domain and frequency domain. So same non-zero indices for the sparse matrices. Due to this sparsity pattern, we have selected sparse Bayesian learning framework as a conventional algorithm to improve the channel estimation at low SNRs for the sparse channels in the considered site. And this is all the received signals you see during M training intervals. And these all pilot signal, transmit precoders, these are all known. And so we can assume these matrices are all known at the receiver. This is the dictionary matrix, and it's also known, but constructed with fixed grid. One problem with grid, selecting grid points is that it should not be too high. We both need sufficiently high number of grid points to improve the channel estimation, but also not too much, because otherwise computational complexity becomes a concern. So actually, we use block sparsity to exploit this, and also use actually sufficiently high number of grid points, but not too much. So it's a trade-off. And also we will use different grid points during offline training and testing. We will use the training data just for a grid construction algorithm. But in testing stage, we actually start a conventional sparse Bayesian learning algorithm. So this algorithm can also be run without learning the priors from the training data. And this, we have a sparse vector here, and this is the proposed framework. And now we are considering testing stage, not consider any training data, but directly focus on the testing stage. The first step, we consider the time domain signals, because we use the sparse channel characteristics, and using some thresholding, we eliminate some taps, some actually time delay taps. Using this, our aim is to improve the SNR. So, and also use a small number of delay taps, not using all the frequency domain subcarrier channels. Instead, use the time domain signals, keeping only a subset of delay taps. And in the next stage, we also apply the whitening, because the noise is colored due to the receive combiner. And so we have a now white noise model here. And also these matrices are known, and we have a sparse vector. So this is the proposed pattern coupled sparse Bayesian learning framework. And here we will introduce sparsity connections between both consecutive angle of arrivals and angle of departures. Because we have observed there is some relation in the true channel between the consecutive points, grid points. And also we will model the hyperparameters to exploit the common sparsity. Actually, this paper is just a general framework. It's a signal processing paper, but we will use our learned things from this challenge problem and incorporate this information to our problem. Okay, so these are the matrices. And in the proposed pattern coupled approach, these are some details, but we model the pattern coupling. between the different hyperparameters in the sparse Bayesian learning framework. So these are some theoretical details. And at the end, we use an expectation maximization algorithm and also use the SNR range. It's provided, and it's an iterative algorithm, and closed form, all closed form update solutions are provided, only one suboptimal update state. So these are actually easy to handle. Also, we only use CPU in this method. And at the end, we learn the joint relations. We can learn the joint relations using this algorithm for the training data also, using the channels in the training data. But it's not compulsory, but just improve the estimation accuracy. And apply a grid construction algorithm. You see, this is for the considered site-specific area, but it's actually power pattern heat map for the power distribution of the sparse vectors between the angle of arrival points and angle of departure points. We construct a grid construction algorithm so that we are not use uniform grids to improve the channel estimation in the testing stage. Instead, we are applying some tricks and ideas here to obtain a good grid construction algorithm. And these are the results. And in this challenge, more weight is given to the challenging scenarios. And this is our final performance score in terms of normalized mean square errors. And thank you for your kind attention. And I would be glad to answer your questions.
Thank you. I want to ask, you mentioned about pilot strength, and I remember that Nuria had different weightage for pilot based on pilot strength based on the SNR. So I want to ask, how could you explain this table, how you are performing with respect to the different SNR values, please?
Actually, only these SNR values, SNR range information is provided. So there are 3 SNR ranges, and the channels in the test data set are actually the SNR can be any value between these values, these ranges. Also, in the left column, we see different pilot lengths. So we can only use this amount of received signals. So in this case, this is the most challenging scenario because SNR is too low, and also we can only use 20 received signals. But this information actually is already handled because our algorithm, since it's not a deep learning algorithm, is independent of the pilot tank. So we simply obtain the matrices and implement the algorithm. For the SNR range, we use this information. But we can also arrange the algorithm not to use this specific information, but since it is provided to improve the channel estimation, we have used and assume a uniform distribution in DB domain, logarithm domain.
Thank you. I want to ask about your model structure. Could you yes, somewhere you were explaining this. Yes, could you briefly tell us, like, what is the structure of your model? I might have missed it.
Yes, because probably I have introduced a lot of theoretical details here. But the idea is that normally the aim is to estimate the frequency domain channels, but using inverse DFT and DFT, we can convert to the time domain or frequency domain. But since in time domain, there is also a sparsity, in our algorithm, we are not using all the frequency domain channels. Instead, use inverse DFT and use time domain channels, time domain information. But using some thresholding, we eliminate some delay taps. Because in theory, they only consist of noise. But since SNR is too low, of course, we cannot detect easily this thing. But this is just based on our observation on the training data through channels. But using some thresholding, power thresholding, we keep only the dominant delay taps and apply the algorithm to that. And also this doesn't change the algorithm since there's a common sparsity and this is already modeled in the algorithm. And the other step is just whitening the noise for our sparse Bayesian learning framework.
Thank you. Final call for judges. Thomas is here. I want to ask a really simple question. What is the relationship with autonomous systems? I think your group is called autonomous systems.
Yes, because actually this challenge problem is not directly related to our funding agency, because we are from communication, we are communication people basically, but for the deep learning for communication, just WASP funded us actually for a specific project about self-reading massive MIMO.
I see. Interesting.
So not directly related.
Interesting. Okay. We thank the speakers. Thank you so much. Back to you, Thomas.
Thank you very much.
Thank you so much to the speakers, and thanks to Vishnu for the moderating the Q&A. Right now, we are going to the last presentation, of course, not the least. We have Lane Chester.
Good evening, everyone. Our team name is Learn Chester, and our topic of presentation is a multi-level greedy and Bayesian compressive channel estimator for frequency selective hybrid MIMO systems. We consider a millimeter wave hybrid system whose block diagram is shown here. The pilot signal S is first baseband precoded and converted to using a matrix FBB, then transformed to time domain using the OFDM modulation, then up converted to RF domain, then RF precoded and transmitted over the air via NT-X1, NT transmit antennas. The received signal using NR antennas is combined using RF combiner, then down converted using RF chains, then transformed to frequency domain and baseband combined to get received signal y of k. K denotes subcarrier index here. And we adopt a extended virtual channel model similar to the one used by previous two teams. D delay tap is decomposed as three matrices, AR, del, DV, and AT Hermitian, and number of taps are totally NC number of taps. When we go to the frequency domain, channel is decomposed as H of k is taking a DFT of this delay domain matrix. It gets transformed as AR, that is the receive array steering matrix, then matrix del VK, which is the path gain matrix, and matrix AT Hermitian, which is the transmit array steering matrix. The AR matrix is of size NR cross GR, AT is of size NT cross GT, and the number of non-zero components in del V of k is much less than the number of dimensions of this matrices AR and AT. That's why it's a sparse matrix. We transmit M training frames, and when we restructure the received signal as a matrix form, the kth subcarrier's received signal vector y is actually equal to phi. Phi is a matrix that contains the pilot signal, RF precoder, and RF combiner, and the sparsifying dictionary matrix psi, which contains AT conjugate of AT Kronecker product with AR, and a vectorized form of the matrix del V, plus a colored noise because of the RF combining at the front end. So many sparse signal recovery algorithms work well with the noise is white. So we do a noise whitening at the front after in the baseband side. So we compute the covariance noise covariance matrix, which has a block diagonal form. And the block diagonal elements depend on the RF combining matrices, which are known a priori at the receiver. We do a Cholesky decomposition, and we multiply this dW inverse and conjugate transpose of that to get an equation phi W psi HV of k plus NW. Noise here is a white Gaussian noise here, which means the identity covariance matrix is identity in this case. Now we concatenate, this is for the kth subcarrier. Now we concatenate all k subcarriers received signal as a matrix to get YW, which is phi W psi into HV. HV now is a row which contains the channel of all subcarriers stacked in as columns. And since the angle of departure and arrival are independent of the frequency index, this HV has a joint row sparse structure. That means the indices of non-zero elements are same across each column. And here phi W is known. It depends on the RF combiner pilot signals. Psi is not known. One good way to initialize psi is to use a DFT matrix because it is good. It's appropriate for uniform linear arrays with lambda by 2 antenna spacing. And we use a dictionary size of GR and GT as 2 power 8, 2 power 8. So our psi matrix will be of size 65536. A number of columns are 65536. Now our goal is to estimate this HV given by W and phi W. This is the outline of the proposed solution. We input the received noise weight and received signal plus a measurement matrix phi W. There are 3 stages. First stage is the dictionary learning stage. That is these 2 stages. It's based on SWOMP. SWOMP is simultaneously weighted orthogonal matching pursuit. We have a new variant of that. Novelty is basically on this refining this dictionary in each step, each iteration of this algorithm. Second stage is sparse Bayesian learning stage, which is used for estimating the sparse matrix. And finally, we transform this frequency domain channel estimates through lag domain, and we have a denoising filter to remove the noise from this channel estimates, and we output the channel. Some of the important aspects are the algorithm is fast because it is based on a greedy search. It's pretty fast, and we integrate it with a high-performing sparse Bayesian learning approach. And as I said earlier, it has 3 stages. SWOMP is used for reducing dimension of the problem. Then estimation is done by SBL, which uses expectation maximization. It's a statistical inference approach to pose the estimation problem as an optimization problem. Since it is non-convex, we bound the cost function by a convex lower bound and maximize the lower bound. And it is known to converge to a stationary point of the original cost function. And finally, we have a denoising in the delay domain. And we also have a mathematical model to model the off-grid effects to recover the angle of departure and arrival outside this quantized beam space. We show empirically that it works in practice, but we are yet to provide mathematical guarantees, and there is scope for further research in this domain. And our algorithm uses sparsity in both beam space, that is the angle of departure and arrival space, also in delay domain. And it is known to converge to a stationary point or a local optimum of the original objective function. The details of the algorithm is here. The first stage is multi-level greedy search stage. The inputs are the noise weight and received signal, measurement matrix, an initial estimate of this dictionary, that is a DFT matrix, and some parameters N and S, which were learned using the training data available. So we initialize the support set as null sets initially. The main step is this argmax step, which projects the received signal onto the columns of this dictionary and picks the column that has a maximum correlation. So once we choose a particular column with maximum correlation, we extract the angle of arrival and departure. Then we expand the dictionary around the chosen angle of arrival and departure. And we go back to the previous step and refine the estimate further. So we do it n times. N is fixed based on a complexity performance trade-off. We choose n as 5 times here. And delta of theta and phi are chosen based on the training data. And once we estimate this psi hat, one tap of the channel is estimated here. And once we estimate this psi hat, we again concatenate the chosen angle in the dictionary matrix and compute the psi hat as a Kronecker product of AT and AR hat. Then we compute channel estimate HV. Then we subtract the contribution of the current channel estimate from the received signal and go back to the first step. At the end of this, we repeat it S times. S is chosen based on the offline data available while training. So at the end of the algorithm, we would have chosen AR matrix, which has S columns, AT matrix, which has S columns, and psi matrix, which has S squared columns. So output dictionary will be having S squared columns, and we also compute noise variance using the residual here. We just compute the Frobenius norm and then normalize it to find the noise variance output. The last stage is sparse Bayesian learning stage. It has 2 steps. The inputs are the original received signal and the estimated dictionary from the previous step and noise variance. And we treat the channel as hidden variable with complex Gaussian prior with mean 0 and covariance gamma. Gamma is basically diagonal of this small gamma. And hyperparameters gamma is used to promote row sparsity in this case. There are 2 main steps. One is expectation step and maximization step. This step is used to compute channel estimate, and M step is used to compute the hyperparameters. This E step is used to compute a lower bound to the original cost function. That is that it uses Jensen's inequality to compute the lower bound. Expectation of log likelihood function with respect to a posterior distribution of the channel given the previous hyperparameter update. Then there is a M step which will maximize the lower bound. We repeat this till convergence. Since it follows the evidence lower bound maximization approach, that is bounding a non-convex objective function by a convex lower bound and maximizing it, it is known to converge to a local optimum of the original cost function. So once we get this HV hat, then we go back. This is in frequency domain. Then we go to the time domain to get time domain channel estimates. Then we threshold based on the noise variance obtained using the offline data available. We fix the number of dominant taps to be output to be used from this noisy estimate. Then based on that, we compute the noiseless, we denoise the signal and finally output this channel estimate. And coming to the results here, this shows the NMSC results of our on-test data sets for 3 different SNR values and 3 different pilot number of frames. And our final score is minus 9.16 dB, and it is based on the 20 pilot frames NMSC results. Our references are these papers, and our code and report are available in this GitHub website. Thank you.
Okay, I had a couple of clarifying questions. A very basic one first. Why do you call this a hybrid approach?
Yeah, let me go to the first slide. Generally, in millimeter wave channels and communication systems, this precoder here won't be available. The whole precoding will be done at the baseband side. But since in massive MIMO systems, the number of antennas are quite large, and if we use 1 RF chain per antenna, the power consumption will be very huge. To reduce that, we have an RF precoding and RF combining stage, which will reduce the dimension of the signal at the input and the output here. So in this case, we can use less number of RF chains. That will reduce the power consumption. That is the main reason why this hybrid architecture is used.
Okay. I want to ask about in your flowchart. So yeah, you had the flowchart where you had
this one.
No. In the sparse Bayesian below, I think. Yeah. So the hyperparameter update. What is happening for the hyperparameter updates, and how do you choose? Could you explain again what happens for the hyperparameter update, and how much does the convergence cost us in terms of time and iterations? I'm trying to find the equivalent of what we call as a training time, right? This is, or did I understand it correctly? Could you explain?
No, this is for the test data as well as training data. Generally, SBL is a computationally complex algorithm because it has an inverse here. There's an inverse present in this sigma by inverse. But since in our case, we have a dictionary learning stage, which will reduce the dimension of the problem. So the size of the inverse will get reduced, which will reduce the complexity of the algorithm. In that case, I'm saying that it's fast. The hyperparameters are nothing but we impose a prior on this original channel we want to estimate. That is called a hyperparameter. If I'm telling correctly, or if Chandra wants to answer, then
yeah. I mean, so sparse Bayesian learning itself is a very well-known technique for sparse signal recovery. What you do is you assume that this is a fictitious prior. You assume that every entry of the sparse vector is Gaussian distributed with mean 0 and an unknown variance. And in the algorithm, using the data itself, you try to find the ML estimate of the variance. It turns out that the cost function is such that when you try to estimate this variance, a lot of the variance estimates end up going to 0. And as a consequence, when you try to estimate, find a posterior mean estimate of a Gaussian, whose mean is 0 and variance is also 0, the posterior mean will be equal to 0. So a lot of the entries of the sparse vector you finally estimate will be zeros. And that's how imposing a Gaussian prior with 0 mean and unknown variance, which you estimate from the observations itself, actually leads to sparse solutions.
And this also depends upon the dictionary estimation, I guess, right?
Right, yeah. So psi hat is the dictionary that was estimated in the previous step, and that is an input to this algorithm. Yes.
Okay, okay.
So errors in the dictionary can lead to solutions that are maybe not quite as sparse as you wanted them to be.
Here you say until convergence. What does that mean? How many? And you told us it is computationally intensive. What exactly does that mean?
Because this sigma y is of psi, we have an inverse, and the order of inverse will be cubic in complexity.
No, what I mean to ask is, in your training and validation, how many iterations, how much time are we talking about here?
I chose because of, just while training I chose while testing I chose S equal to 10. That means this dictionary will be of size, will have 100 columns. So this matrix will be of size 100 plus 100. And we ran in normal PC, not in GPU. And the number of iterations it takes to converge will be around 50 or something. 50 odd iterations to converge.
Okay. There is our friend Thomas is here. Thank you, Sai, and thank you, Chandra, for the explanations. Back to you, Thomas.
Thank you for having us.
Thank you so much, Vishnu, and thanks to all the presenters in today's pitching session or today's presentations. Thank you so much. From me and my colleagues at ITU AI and Machine in 5G, I wish you a very good day. Thank you and bye-bye.